For decades, humanity's gaze has been fixed on the farthest reaches of space. Our most powerful instruments have spent the better part of a century peering into the cosmic abyss, chasing black holes, charting the lives of dying stars, and mapping the very edge of the observable universe. Yet, in this grand survey of the cosmos, we overlooked what was closest. Just over 4 light-years from Earth is Alpha Centauri, our nearest stellar neighbor, and until recently, it remained largely unexamined. The James Webb Space Telescope changed that. What it uncovered orbiting the system's 3 stars is compelling scientists to rethink fundamental ideas about how planets form and to entertain a possibility that was never anticipated so near to our own world. In the final weeks of 2023, new instructions were transmitted to the James Webb Space Telescope. Its target was not a remote galaxy or some cosmic enigma billions of light-years away, but Alpha Centauri, a mere 4.37 light-years from Earth. This is our closest stellar system, a distance so vast, yet so intimate, that a person walking at 3 miles per hour would need roughly 80 million years to arrive. Historically, this system was deliberately avoided by other observatories, including a fleeting glance from Hubble. The reason was simple: it was too bright and too close. The intense radiance from its 3 stars created an overwhelming glare, much like trying to read a newspaper while facing a floodlight, drowning out any faint objects nearby. But Webb perceives the universe differently. Its instruments are sensitive to infrared vision, allowing it to detect the subtle heat signatures that are invisible to the human eye. It can see through cosmic dust and pierce the very glare that hides so many secrets. The initial observation required a 14-hour exposure. The scientific team anticipated the results would be fairly standard, perhaps a sharper image of Proxima Centauri, the system's smallest star, or a confirmation of planets already known to exist. They received neither. Instead, the data stream revealed something entirely unforeseen within the habitable zone around Proxima. It was a distinct and unambiguous signal, corroborated across 3 of the telescope's independent instruments. Dr. Sarah Chen at the European Southern Observatory was the first to analyze the transmission. After verifying the calculations multiple times, she contacted her supervisor in the early hours of the morning. She reported that they faced a significant issue, not because the data was flawed, but because it was correct and profoundly puzzling. The signature had appeared in the mid-infrared spectrum at wavelengths between 5 and 12 micrometers. This portion of the spectrum is crucial for understanding the composition of an atmosphere, revealing what gases are present, the temperatures they maintain, and the chemical processes occurring in the delicate layer between a planet's surface and space. Webb was able to discern all of this with an unpredicted level of detail. The most startling revelation was that the planet, known as Proxima Centauri B, was not merely located within the habitable zone. It displayed signs of active atmospheric processing, with temperature gradients, pressure variations, and patterns of heat distribution that strongly suggested the existence of weather systems. This was evidence of real weather, with clouds forming, circulating, and dissipating in what appeared to be a hydrological cycle. This world was first identified back in 2016 using the radial velocity method, a technique that involves measuring the slight gravitational pull a planet exerts on its star, causing it to wobble. From this, scientists had determined its mass to be about 1.3 times that of Earth, and its orbital period to be a swift 11.2 days, placing it squarely in the zone where liquid water might exist. But until this observation, its atmosphere had never been directly seen. The new information showed a vertical structure within the atmosphere, with distinct temperature layers at varying altitudes. On our own planet, such layering is the result of a complex interplay of forces, including solar heating, the convection of gases, the movement of moisture, and chemical reactions, all working in concert. To find this on Proxima B suggested something remarkable. This wasn't a static ball of rock, it was a dynamic world, alive in a geological sense. However, the subsequent data made the scientific community question everything they thought they understood about this system. In astronomy, brightness can ruin an observation. Pointing a telescope at an object that is too luminous often yields nothing but glare. The Alpha Centauri system presented a triple threat of luminosity, all wrapped into one cosmic package. Alpha Centauri A shines with 1.5 times the luminosity of our own Sun. Though 25 trillion miles away, it is still visible from Earth's southern hemisphere with the naked eye. Its companion, Alpha Centauri B, glows almost as brightly, and the two stars are locked in a gravitational dance, completing an orbit of each other every 80 years. Then there is Proxima, the small red dwarf, which, despite being dimmer, is still bright enough to mask any nearby Earth-sized worlds in its light. An attempt by the Hubble Space Telescope in 1995 yielded images showing only two indistinct blurs of light, with no planets or details visible. The overwhelming radiance simply saturated the sensors, akin to pointing a camera directly at a car's headlights and hoping to see the vehicle's frame. It was impossible. Ground-based telescopes struggled even more. Earth's own atmosphere creates distortions, as rising heat causes starlight to wobble, and water vapor scatters infrared signals. By the time light from Alpha Centauri reached a terrestrial telescope, it was scrambled and blurred, making detailed planetary observation useless. While adaptive optics and laser-guide stars brought improvements in resolution, they could not fully pierce the glare. The development of the coronagraph was a major step forward. This instrument effectively creates an artificial eclipse within the telescope, blocking the direct light from a star. Early versions were imperfect, as light scattered around the edges and diffraction patterns leaked through, allowing the glare to persist. Modern coronagraphs, however, have become far more sophisticated. The one aboard James Webb is specially engineered for infrared wavelengths, designed to filter out visible starlight while allowing thermal signatures to pass through. For years, there was considerable debate among scientists about whether Alpha Centauri warranted any of Webb's valuable observation time. Access to the telescope is fiercely competitive, with thousands of proposals vying for a limited number of slots. Many argued against wasting time on nearby stars, when distant galaxies and black holes held so many cosmic mysteries. The consensus began to shift in 2022. Computer models increasingly suggested that Proxima B could potentially hold on to an atmosphere, even with the intense stellar flares from its parent red dwarf. Perhaps it was worth a look. Ultimately, the James Webb team dedicated a 14-hour window to the observation, making sure every moment counted. They timed it to coincide with a known quiet period for Proxima. Red dwarfs are notoriously volatile, frequently erupting with radiation that can strip atmospheres from planets, but they experience lulls when this fury pauses. Webb captured one of these windows under ideal conditions, yielding flawless data. The combination of Webb's infrared sensitivity and its advanced coronagraph overcame the obstacles that had stymied astronomers for decades. Instead of looking for faint, reflected starlight, Webb detected the warm, intrinsic glow of the planet itself. With their infrared sensors focused on cooler signatures, a new picture began to emerge. Suddenly, after long decades of technological blindness, scientists could finally perceive what was hidden in the space nearest our own. What they discovered was not a single, isolated planet. It was an entire cosmic system, far more intricate than anyone had previously conceived. A system containing 3 stars is something that seems to violate the rules. It certainly challenges the old understanding of celestial mechanics. Before the discovery of planets in the Alpha Centauri system, our models of planetary formation suggested this arrangement should not be possible. There was simply too much chaos. The gravitational influences were too numerous. The stellar radiation from multiple suns was too intense. Planets require stability to come into being. They need a calm environment. They need an immense amount of time. The Alpha Centauri system appears to offer none of these conditions. Alpha Centauri A and Alpha Centauri B swing around a common center in a long, elliptical path. When they are nearest each other, their distance is a mere 11 astronomical units. This is roughly the same distance that separates our own Sun from Saturn. At their farthest point, they stretch out to 35 astronomical units, a distance comparable to Pluto's orbit. This dynamic creates a gravitational landscape that is in constant flux. Any material attempting to coalesce into a planet within this region would face perpetual disruption. Proxima Centauri is situated much farther away. It lies 13,000 astronomical units from the central pair. Its true relationship to the other two stars is still debated by some astronomers. Perhaps it is only a temporary neighbor, just passing by. It is possible that it completes one orbit every 500,000 years. It might be gravitationally connected, but only by the thinnest of threads. No one can say with absolute certainty. This ambiguity is significant. It has a direct impact on our models of how planets form. When stars are born, they collapse from immense clouds of interstellar gas and dust. This material naturally swirls into a flattened, rotating disk. Within this disk, tiny particles begin to collide. Over millions of years, they stick together, slowly building the worlds we see today. However, this accretion process requires a consistent environment. If the gravitational field changes too dramatically, the collisions become destructive rather than constructive. Particles are more likely to shatter each other than to accumulate into larger bodies. Three stars introduce three distinct gravitational fields. They provide three sources of radiation that heat the protoplanetary disk. They also generate three separate stellar winds, pushing the gas and dust around. Computer simulations from the 2000s indicated that planets could not form in such a place. The environment was considered far too violent. Any planetary embryos would be scattered into deep space. They might be ejected from the system entirely, or they could be destroyed before they grew massive enough to hold themselves together. Then, a discovery changed everything. In 2016, a planet was confirmed using the radial velocity method. It was named Proxima B. It had 1.3 times the mass of Earth. It orbited within its star's habitable zone. This finding compelled astrophysicists to rethink their assumptions. If one planet could exist there, perhaps others could as well. Maybe the perceived chaos was not chaos at all. It could be a different type of order, one we had not yet learned to recognize. Observations from the James Webb Space Telescope offered an explanation for how these planets survived. The three stars did indeed form together. However, Proxima separated from the main pair at an early stage. This happened before the planet formation process was complete. This separation effectively gave each star its own zone for planetary development. Alpha Centauri A had the space it needed to form its own worlds. Alpha Centauri B was granted its own distinct region. Proxima, now far from the central pair, could develop its planetary system in relative peace. But in space, isolation is always relative. Every 79. 9 years, Alpha Centauri A and B complete their orbit and swing close together. This periodic event creates gravitational ripples that travel throughout the entire system. These are not massive, world-shattering disruptions. They are just enough to stir the cosmic dust. They are enough to clear out certain orbital pathways. They are enough to make planet formation difficult, yet not entirely impossible. The planets that manage to survive now occupy very stable zones. They are like safe harbors in an otherwise turbulent cosmic sea. The Webb telescope detected these zones by observing in the infrared spectrum. Patterns in temperature revealed where dust was concentrated. They showed where gaps had been carved out. They illustrated how gravitational resonances created an underlying structure. The system appears organized today, but that organization was achieved at a great price. For every single planet that survived, it is likely that dozens of others were ejected into the lonely expanse of interstellar space. The fortunate few remain, and these lucky survivors hold even more surprises than anyone had anticipated. Its mass is 1.3 times that of Earth. It orbits 7.5 million kilometers from its star. Its orbital period is just 11.2 days. These are the numbers that define Proxima B. They also define a sense of hope. This is because the world resides in the precise region where liquid water could potentially exist. It is not too hot, and it is not too cold. It sits within the habitable zone. Red dwarf stars make the concept of a habitable zone quite tricky. They burn at a much cooler temperature than other stars. Their surfaces are around 3000 Kelvin. This is in contrast to the 5700 Kelvin surface of our own Sunday. This lower temperature means that any planets must orbit very close to their star to stay warm. They must be incredibly close. Proxima B huddles near its star, much like a person standing next to a campfire on a frozen night. If you move too far away, you freeze. If you get this close, you risk being burned. This proximity introduces other challenges. One major issue is tidal locking. Gravitational forces have locked one hemisphere of the planet to permanently face its star. This side experiences constant day. The other hemisphere is turned forever toward the cold of space. It is a land of eternal night, always dark and always frozen. This phenomenon is common throughout the universe. Our own moon presents the same face to the Earth. The planet Mercury is nearly locked in its orbit around the Sunday. If you get close enough to any massive object, your rotation will eventually cease. The tides always win. For a long time, scientists debated whether a tidally locked planet could ever support life. One side bakes while the other side freezes. Where could a middle ground possibly exist? Computer models began to suggest a potential answer. The key was an atmosphere. A sufficiently thick atmosphere can transport heat. Winds can carry warmth from the day side over to the night side. Ocean currents can also help distribute the temperature more evenly. The planet does not necessarily need to rotate. What it needs is circulation. The James Webb Space Telescope saw evidence that this is exactly what is happening. Temperature readings of the planet revealed a significant distribution of heat. The day side measured approximately 300 Kelvin. This is hot, but not scorching. The night side dropped to about 230 Kelvin. This is cold, but not frozen solid. The terminator zone, the boundary between day and night, held steady near 270 Kelvin, a perfect temperature for liquid water. This temperature gradient was proof of atmospheric transport. Without an atmosphere, the day side would roast at a blistering 600 Kelvin. The night side would plunge to a frigid 50 Kelvin. The only habitable area would be the terminator itself, a narrow ring circling the globe. But the data from Webb showed something else entirely. The heat was spreading. The cold was being moderated. Something was actively moving thermal energy around this distant world. The planet's mass is a critical factor here. A mass of 1.3 times that of Earth means it has stronger gravity. Its gravitational pull is about 20% stronger than our own. This gravity helps the planet hold onto its atmosphere. It protects it against the star's powerful stellar winds and radiation. Proxima Centauri is known to erupt with violent flares. It emits powerful X-ray bursts. It floods its surroundings with ultraviolet radiation. Each one of these flares can strip away particles from a planet's atmosphere. Lighter planets tend to lose their air very quickly. Heavier planets are better at holding on. Proxima B sits right on a crucial threshold. It is just massive enough. It holds on, but just barely. Scientists have calculated the timescales for atmospheric retention. They asked how long it would take for the star's flares to strip everything away. The results were surprising. The atmosphere could last for billions of years. It might persist for 4 billion years. It could last even longer, if the planet has a helpful magnetic field. This world has had time. It has had time for complex chemistry to evolve. It has had time for intricate processes to develop. An unexpected discovery was about to emerge, but the true revelation was not the world itself. The real surprise lay in what the Webb telescope detected within the planet's atmosphere during that initial observation. The science of spectroscopy is what uncovers such truths. As starlight journeys through an atmosphere, it becomes filtered, causing certain wavelengths of light to disappear from view. Molecules in the air absorb very specific colors, leaving behind a pattern of dark lines in the resulting spectrum. To read those lines is to read the chemical makeup of the atmosphere, revealing the gases that drift in that alien sky. Webb aimed its near-infrared spectrograph at Proxima B during one of its transits. As the planet moved across the face of its star, the starlight passed through the atmosphere at the planet's edge. The instrument gathered that filtered light, carefully analyzed it, and broke it down into its constituent wavelengths. The spectrum that resulted was so profound, it gave the science team pause. 3 absorption features were immediately apparent at 730 nanometers, 1,400 nanometers, and 1,900 nanometers. These specific wavelengths are telltale signs of particular molecules. The first line was a match for both oxygen and water vapor. The second corresponded to water vapor by itself. The third indicated a combination of water vapor and methane. All 3 of these signatures appeared distinct, powerful, and undeniable. At MIT, Dr. James Peterson was reported to have run the analysis 4 separate times. He later recalled his persistent thought that his team must have somehow contaminated the data. In an interview, he explained that the signature was simply too clean and obvious, almost as if the planet had wanted to be found. His team meticulously investigated any possibility of instrumental errors. They searched for potential contamination from the star itself. They even checked for cosmic ray impacts that could have corrupted the data. They found nothing. The signature was genuine. The presence of water vapor in the atmosphere of an exoplanet is no longer a shocking find in itself, as Webb has identified it on dozens of other worlds. What truly matters, however, is the quantity. The concentration and distribution of these molecules are key. Proxima B's upper atmosphere showed a water vapor concentration of 7 parts per thousand. By way of comparison, Earth's atmosphere averages about 4 parts per thousand. This distant world appeared to hold more moisture in its air than our own. The oxygen line, however, was a source of confusion for everyone. There are 2 primary scenarios that can lead to oxygen in an atmosphere. One is chemical, the other is biological. The chemical process occurs on worlds bathed in large amounts of ultraviolet light, which can break water molecules apart. The lighter hydrogen then escapes into space, leaving the oxygen behind. But Proxima Centauri emits less ultraviolet radiation than our Sun, not enough to split water with such efficiency. And yet, the spectrum confirmed the presence of oxygen. The existence of methane made the situation even more complex. Methane and oxygen, when found together, create what is known as a disequilibrium. These 2 gases naturally react with one another and, over time, they are mutually destructive through chemical reactions. To discover both of them at the same time implies that some process must be constantly replenishing them. Something is producing these gases at a rate faster than chemistry can remove them. On our own planet, this role is filled by biology. Plants generate oxygen, while microbes produce methane. Life itself is what establishes and maintains this chemical imbalance. Chemistry tends toward equilibrium, but life actively works against it. The simultaneous presence of both gases, in significant amounts, strongly suggests an active source of replenishment, something continually generating these molecules. But a suggestion is not the same as proof. The scientific community needed more data. They required confirmation from different instruments and multiple observations. A single spectrum, however compelling, could be an anomaly, a misinterpretation, or an instrumental artifact. The scientific method is built on a foundation of skepticism and demands thorough verification. The Webb team scheduled a series of follow-up observations, covering 6 more transits over the next 8 months. Every new observation added more data, and each resulting spectrum seemed to reinforce the first. With every new dataset, the enigma only grew deeper. The planet's atmosphere should have been stripped away by stellar flares. Proxima Centauri erupts with regularity and violence. Every few months, a powerful flare explodes from its surface, causing a surge of radiation. The system is flooded with X-rays and spikes of ultraviolet light. Each of these flares strikes Proxima B with enough force to blast thousands of tons of its atmosphere out into space. Red dwarf stars are notoriously violent. They remain active for trillions of years, continuing to erupt and flare long after other stars have settled down. Our own sun will one day expand into a red giant and then fade into a white dwarf. But Proxima will continue to burn, flare, and batter any planets in its vicinity. To put this in perspective, Proxima's flares can increase its brightness by 20%. If our sun were to suddenly become 20% brighter, the change in temperature would be catastrophic for Earth. Proxima B orbits in the direct path of these eruptions, just 7.5 million kilometers away. When a flare occurs, the radiation reaches the planet in only 25 seconds. There is no warning and no time to prepare, only the immediate impact. This flux of ultraviolet and X-ray radiation heats the upper atmosphere, causing gas molecules to gain energy and move faster. Some of them achieve escape velocity and are lost to space. The atmosphere should, particle by particle, eventually disappear. Scientists had calculated how long Proxima B could possibly hold on to its water vapor under such hostile conditions. Their models suggested a time frame of 50 million years, or perhaps 100 million if the planet began with a truly immense atmosphere. But Proxima B is 1.5 billion years old. By all accounts, the water vapor should have been gone for eons. The atmosphere ought to be a mere whisper of heavier gases clinging to the surface. Instead, Webb had detected robust concentrations of 7 parts per thousand, an atmosphere that was thriving and persistent. Some mechanism had to be protecting this atmosphere. Some process was preventing it from bleeding away. The first theory centered on magnetic fields. Earth's magnetic field acts as a protective bubble, deflecting the solar wind and funneling charged particles toward the poles, which results in auroras rather than atmospheric destruction. It was possible that Proxima B possessed a similar shield. A second theory proposed a process of atmospheric replenishment. Perhaps the planet was constantly generating a new atmosphere through volcanic outgassing, or from water being released from subsurface reservoirs. This would involve chemistry producing new molecules to replace those that were stripped away, creating an endless cycle where loss is balanced by production. The third theory was one that made some uncomfortable. It suggested that perhaps we had simply underestimated the effects of stellar flares. Maybe the existing models were flawed, and atmospheric escape happens more slowly than previously calculated. This theory would require an admission that earlier work contained errors, something scientists are hesitant to do. But the data compels honesty. Webb's continued observations provided crucial clues. During one of the transits, Proxima Centauri happened to erupt with a moderate flare. The telescope captured the entire event, measuring exactly how the atmosphere responded. Did it get blown away? Did it compress? Did the radiation strip particles into space? The data revealed a fascinating response. The upper atmosphere grew darker. Heavier molecules appeared to rise from below, absorbing the incoming radiation. It functioned much like Earth's ozone layer, which blocks ultraviolet light. When the flare struck, the atmosphere effectively shielded the surface below. After the flare had passed, the absorption faded, and the atmosphere returned to its previous state. It was a demonstration of resilience adaptation, and protection. This single observation fundamentally changed the calculations. If a planet's atmosphere could actively respond to stellar flares, its rate of atmospheric loss would decrease significantly. This resilience could allow the planet to hold onto its water vapor for billions of years. It might keep its reservoir of air completely intact. It might even remain habitable, despite the violent celestial events overhead. This potential for resilience, however, raised new questions. How could a planet ever develop such an effective form of defense? Was its origin a matter of random chance, or was it something more deliberate? Patterns in data carry information. Random noise simply creates chaos. By contrast, organized signals produce structure. The Webb telescope detected just such a structure in the mid-infrared emissions from Proxima B. It was a repeating pattern. The pattern recurred every 11.2 hours. This timing exactly matched the planet's rotational period relative to its orbit. The signal itself appeared at a wavelength of 4.5 micrometers. This particular range points to heat being radiated from warm surfaces. The temperature was estimated to be around 350 Kelvin. This was warmer than the average temperature on the planet's day side. It was also warmer than scientific predictions had suggested. And crucially, the signal pulsed. Its brightness would increase for 2 hours. Then it would drop for 2 hours. Then it would increase once more. The rhythm was as regular as clockwork. Dr. Maria Santos at the Max Planck Institute was the first to notice it. She said she initially thought the instrument was malfunctioning. Planets, she explained, are not supposed to pulse. They should glow with a steady, even light. This strange behavior looked artificial. She worked to isolate the signal. She removed any contamination from the star's light. She subtracted all the background noise. The pulse remained. It was strong, clear, and undeniably real. 3 possible explanations began to emerge. The first possibility was volcanic activity. Active volcanoes are known to produce infrared hotspots. If Proxima B had a massive volcanic region, this region would rotate into and out of view. This movement would create a pulsing signal. Earth's own volcanic regions glow in the infrared. Hawaii's Kilauea, for example, shows up from space as a bright thermal signature. If one were to scale that effect up to planet-wide volcanism, it could result in noticeable pulses. A second possibility involved atmospheric circulation. Hotspots can form where an atmosphere and a surface interact. Complex wind patterns are able to create significant temperature variations. On Jupiter, the Great Red Spot appears warmer in infrared light. On Earth, deserts glow hot while the oceans remain cool. If Proxima B had an organized system of atmospheric circulation, wind could concentrate heat into specific regions. As the planet rotates, these regions would appear and then disappear from our view. This would create a pulse pattern. The third possibility was that something on the surface was reflective. Perhaps the surface was not uniform. Maybe certain areas reflected more infrared light than others. These could be ice sheets, or metal-rich rocks, or even large crystalline formations. As these reflective regions rotated into view, the amount of reflected heat would increase. When they rotated away, the signal would naturally drop. This would be a result of simple natural variation and geological diversity. But the signal's precision bothered everyone. The period was 11.2 hours, exactly. There was no variation. Pulsars can show this kind of precision. This is because they are neutron stars that have solid crusts. They rotate at an incredibly constant speed. Planets do not work that way. The dynamics of an atmosphere constantly shift. Volcanic activity fluctuates over time. Surface features erode and change. Nothing in planetary science stays perfectly regular over months of observation. The Webb telescope watched Proxima B for 8 months. The pulse never shifted its timing. It never weakened in its intensity. It never changed its phase. Over 1,800 rotations, 1,800 pulses were detected. each one arriving exactly on schedule. This remarkable consistency suggested the source was something stable. It pointed to something permanent. It implied something was fundamentally anchored to the planet's rotation. The team then proposed a fourth explanation. Nobody wanted to state it officially, but in private conversations, over coffee, and during late-night data analysis sessions, people whispered about it. What if the signal was not natural at all? What if it had been engineered? What if something on that world was generating infrared pulses deliberately? Dr. Santos dismissed the idea in her public statements. She told reporters that more data was needed before considering such extraordinary explanations. Privately, however, she kept analyzing the data. She kept looking for patterns within the pattern. She kept wondering what could possibly produce such perfect regularity. She did this because even stranger discoveries were waiting in the data. Magnetism is a key protector of life. Earth's magnetic field deflects solar radiation. It shields our precious atmosphere. It also prevents cosmic rays from sterilizing the surface. Without it, the solar wind would have stripped away our air within a few 100 million years. Our world would look like Mars, dry, dead, and barren. Proxima B needs a magnetic field even more desperately than Earth does. The stellar flares from Proxima Centauri carry immense waves of charged particles. These are radiation storms that make our own worst solar weather look gentle. Without magnetic protection, atmospheric stripping would accelerate dramatically. With that protection, a planet can survive billions of years of bombardment. It is the difference between a world that is habitable and one that is dead. Webb could not measure magnetic fields directly. Magnetism does not show up in optical or infrared light. You need specialized instruments for that, like radio telescopes or polarization detectors. This is equipment that reads how magnetic fields twist light and charged particles. But Webb did see the effects of magnetism. It saw the fingerprints that magnetism leaves behind. During one observation, Proxima erupted with a significant flare. It was a Class M flare, powerful enough to increase the star's brightness by 15%. The wave of charged particles reached Proxima B in just seconds. Webb watched to see what would happen next. The planet's atmosphere responded. Auroras erupted across its surface. They appeared not just at the poles, but across the entire day side. Auroras form when charged particles strike atmospheric gases. The particles follow the lines of a magnetic field. On Earth, they are funneled toward the poles because our field directs them there. The resulting light shows happen in rings around the Arctic and Antarctic. But Proxima B showed a very different behavior. Its auroras spread across the entire hemisphere facing the star. They formed a glowing shield. This pattern indicates a strong and extensive magnetic field. It is likely stronger than Earth's field. It could be 3 times stronger, or maybe even 5 times. This field does not just deflect particles, it also absorbs them. It channels them into the upper atmosphere, where they create this spectacular display. The entire dayside was lighting up like a vast neon sign. Scientists calculated what this would require. A planet needs 2 things to generate a strong magnetic field. It needs a liquid metallic core, and it needs rotation. Earth's iron core spins, generating a dynamo effect. Liquid metal moving through magnetic fields creates electric currents. These currents then strengthen the magnetic field. The field, in turn, influences the metal. It is a self-sustaining feedback loop. But Proxima B is tidally locked. It does not rotate in the traditional sense. One side always faces its star. This lack of rotation means there should be no traditional dynamo. So, how does it generate such a powerful field? The existing models struggled with this question. They required significant modification. Maybe tidal flexing replaces the need for rotation. Perhaps the planet's core sloshes back and forth as it orbits its star. Maybe the constant gravitational squeezing from Proxima generates enough internal movement. it seemed possible that this powerful magnetic field explained several other mysteries. The persistence of an atmosphere around Proxima B, especially with its water vapor and oxygen, presents a compelling puzzle when considering the star's violent flares. The key to this survival appears to be a planetary magnetic field, a shield that deflects the most severe forms of radiation. This magnetic protection significantly slows the rate at which atmospheric gases are stripped away into space. So long as the atmosphere remains sufficiently dense, it can effectively circulate heat across the planet and maintain surface pressure, all while its upper layers are not continuously eroded by stellar outbursts. This single discovery transformed Proxima B from an object of interest into something truly extraordinary. It was a tidally locked planet possessing active magnetic protection, a world that seemed to defy the odds by retaining its atmosphere. Here was a place where the established rules of planetary science appeared to bend. The existence of this magnetic shield also carried a more profound implication for the world below. If the surface is not constantly sterilized by charged particles from stellar flares, then it becomes a place where chemical complexity can begin to develop. The intricate processes of chemistry could evolve without the threat of constant interruption. This means that if life were to exist, it could potentially endure without being scoured from the surface every few weeks, opening the window of possibility for habitability just a little wider. Yet, this magnetic field was not the only protective element at play in the system, and another major feature went unnoticed by astronomers for years. Farther from the star, at a distance of 1.5 astronomical units, orbits the planet Proxima C. This position, roughly equivalent to the distance between Mars and our Sun, means that surface temperatures there drop to a frigid 150 Kelvin. It is a frozen, hostile environment, but it is undeniably real. The planet's presence was first revealed through the subtle gravitational tugs it exerts on its parent star. As a planet orbits, it causes its star to wobble slightly, and these minute movements can be detected through highly precise measurements. Scientists analyzing Proxima Centauri's motion noticed anomalies that could not be explained by Proxima B alone. Something larger and more distant was pulling on the star. Initial estimates suggested an object with about 7 Earth masses, placing it in the category of a super-Earth or a mini-Neptune. Its orbital period was calculated to be 5.2 years, or 1,900 days, a long journey that explains why previous, shorter observation campaigns had failed to capture a complete orbit. The planet had effectively been playing a game of hide-and-seek with existing detection techniques. The James Webb Space Telescope, however, operates differently, as it does not need to observe a full orbit to find a world. It is capable of seeing planets directly by capturing the faint infrared emissions they radiate. Webb's observations not only confirmed the existence of Proxima C, but also measured its temperature and analyzed the starlight reflecting from its atmosphere. The data returned something entirely unexpected: the clear signature of atmospheric absorption lines. This was no barren frozen rock. It possessed a gaseous envelope. The intriguing question was how an atmosphere could persist at temperatures where gases should freeze solid. The answer seems to lie in significant greenhouse heating, where gases such as carbon dioxide and methane trap thermal energy. On Proxima C, this effect creates a warm atmospheric blanket that keeps the gaseous envelope from collapsing, even as the surface remains frozen. This results in an unusual but stable phenomenon known as a temperature inversion, with a cold surface and a warmer upper atmosphere. The planet's composition also puzzled researchers. Models suggested it originally formed as an ice giant, composed of water ice, methane ice, and ammonia ice. Its current location, however, is inside the system's frost line, the boundary where such ices would have been vaporized during formation. This strongly implies that the planet migrated inward, having formed much farther out and moved closer over millions of years, likely nudged by gravitational interactions with Proxima B. Webb, also detected something else around Proxima C, a faint ring system composed of ice particles and dust. These thin rings extend from 40,000 to 80,000 kilometers from the planet and scatter infrared light in a predictable pattern that confirmed their presence. This discovery doubled the number of known planets in the Proxima system, transforming the picture from a single world to a more complex arrangement. Proxima C itself could not support life as we know it, being too cold and too distant from its star. However, it still plays a crucial role. The gravitational interplay between the two planets helps to stabilize their orbits, creating resonances that prevent chaotic changes from destabilizing the system. The existence of a second planet naturally raised an obvious question. If there are two, why not more? Could a third world be hiding in the data, or perhaps an entire system was waiting to be found? This prompted scientists to begin the search for another planet, but what they discovered was not a planet at all. The nearby star Alpha Centauri A is 4.4 billion years old, making it ancient by stellar standards. When a star reaches this age, its primordial debris disk should be long gone, having been either swept clean by stellar winds or incorporated into planets. Only mature worlds should remain. Our own solar system, orbiting a star of similar age, has no such disk. When the Webb telescope pointed at Alpha Centauri A, its goal was to search for planets directly, hoping to spot large gas giants reflecting starlight. Using a coronagraph to block the star's overwhelming glare, its infrared sensors scanned the surrounding space. They found no giant planets, but they did find something unexpected: dust. An infrared emission at 20 micrometers indicated the presence of warm dust grains, with a temperature around 200 Kelvin. Dust this warm must be situated close to the star, somewhere between 1 and 3 astronomical units, which is exactly the region where rocky planets are thought to form. By all accounts, this dust should not exist. 4 billion years of cosmic collisions and gravitational sweeping should have cleared it away. What stood out was that the dust was not a uniform cloud, but showed clear structure, with distinct bands and gaps. This suggested that some unseen force, perhaps gravitational resonances from undiscovered planets, was organizing the material. The gaps were observed at very specific distances: 0.8, 1.4, and 2.3 astronomical units. Scientists calculated the total mass of the dust and found it to be about 1/20th of the mass of Earth. This was a substantial amount of material, far too much to be leftover primordial dust. Its presence demanded a source of active replenishment, meaning something was constantly generating new dust. The possibilities included collisions between asteroids or comets breaking apart. A more radical explanation was that a planet might be forming right now, an idea that would violate every established theory of planetary formation. Planets are thought to form within the first 10 million years of a star's life, after which the protoplanetary disk dissipates. Late formation simply does not happen. The only other explanation was that the disk had been replenished by a recent catastrophic event, such as a collision between two planets within the last million years. The debris from such an impact would spread into a disk and be warmed by the star, creating precisely the kind of young disk around an old star that Webb had detected. The team searched for evidence of a recent collision, such as large debris chunks, asymmetric patterns, or thermal anomalies, but they found none. The disk itself presented a contradiction, appearing smooth and well-organized, which conveyed a sense of great age despite its youth. This paradox invited alternative theories, one of which involved the capture of foreign material. It was conceivable that Alpha Centauri had ensnared a rogue planet or a massive asteroid from interstellar space. Under this hypothesis, immense gravitational tides would have torn the object apart, with the resulting debris gradually settling into the disk we see today. The timeline for such an event is more plausible, as a capture could have occurred as recently as 10,000 or 100,000 years ago, a brief moment on cosmic scales, yet an ancient epoch by human standards. The confirmation of this disk fundamentally altered the strategy for finding planets. If a significant amount of material orbits Alpha Centauri A between 1 and 3 astronomical units, then planets could be concealed there as well. These would likely be smaller, Earth-sized rocky worlds, their presence masked by the dust and the brilliant glare of the star. The sophisticated instruments aboard the Webb telescope possess the capability to detect them should they transit their star. If one of these worlds were to pass between our vantage point and Alpha Centauri A, it would cause a slight, temporary dimming of the starlight. By measuring the specifics of that dimming, a planet can be found. In light of this, scientists allocated 6 months for continuous monitoring, a period dedicated to watching for transits, searching for any dips in brightness, and observing anything out of the ordinary. They did, in fact, find something highly unusual, but it was not what anyone had been anticipating. A fundamental rule of planetary systems is that debris does not orbit in reverse. Everything within a given system is expected to rotate in the same direction counterclockwise when viewed from a position above Earth's North Pole. This uniformity arises because these systems form from immense, spinning clouds of gas and dust. The initial direction of the cloud's rotation dictates the motion of everything that subsequently forms within it. Planets inherit this momentum, asteroids follow the same path, and comets are bound by the same law. All components move together, flowing in a single, unified direction. However, Webb's observations of the debris disk around Alpha Centauri A revealed clear exceptions to this rule. The data showed 3 large fragments moving clockwise, following retrograde orbits that went directly against the prevailing flow. Such a configuration is considered impossible unless an external force had thrown them into these paths. The fragments themselves were estimated to be between 50 and 200 kilometers in diameter. While small by the standards of planets, they are massive for asteroids. Each one was glowing in the infrared spectrum, radiating heat from absorbed starlight, and each one was traveling at the wrong angle, in defiance of all known rules of celestial mechanics. Dr. Jonathan Kim at Caltech, after analyzing their trajectories, uncovered an even more profound peculiarity. He reported that these objects were not simply moving backward. They were locked in perfectly circular orbits. They showed no eccentricity and no wobble, moving with a precision that suggested they had been carefully placed. This is significant because a natural capture event almost always results in elliptical paths. Objects that fall into a star system from interstellar space arrive at random angles and tend to follow chaotic trajectories. These 3 fragments exhibited none of that expected chaos. The circularity of their orbits hinted at a powerful gravitational interaction. Perhaps a close encounter with an undiscovered massive planet had altered their paths, slowing them down and settling their motion into a circle. But such an event would require incredible precision, demanding a planet to be in exactly the right position at exactly the right time, with timing measured in mere years or decades. The probability of 3 separate objects achieving this state by chance verges on the impossible. Another potential explanation centered on collisions. It was possible the fragments originated from a larger body that had been destroyed in a cataclysmic impact. When planets collide, debris is scattered in all directions. Some pieces are propelled forward, some are sent backward, and others can be ejected from the system entirely. The issue with this theory is that collision debris invariably creates elliptical orbits, not the kind of organized, circular paths observed here. The third explanation was one that made researchers uncomfortable. It raised the question of whether the fragments were natural at all, or if something had placed them there. While the idea sounds preposterous, the data compelled its consideration. The existence of 3 objects on 3 perfect circles, all following 3 retrograde paths, pushed the statistical probability of a natural formation to less than 1 in 10 million. Webb also studied the composition of the fragments. Through spectroscopy, scientists identified surface materials including silicates, iron oxides, and carbon compounds, all components of a normal asteroid. There was nothing exotic in their makeup, nothing that screamed of an artificial origin. But an object's composition does not explain its location or trajectory. It only reveals what it is made of. The team then expanded its search, looking for similar objects around the system's other primary star, Alpha Centauri B. They found nothing. There was no retrograde debris and no unusual orbits, only the ordinary, chaotic remnants of planetary formation. The 3 anomalous fragments were found to orbit Alpha Centauri A exclusively, a feature unique to this one star and present nowhere else in the system. Scientists ran extensive gravitational simulations in an attempt to recreate these orbits. They programmed various scenarios, including natural capture events, collision debris patterns, and interactions with a rogue planet. None of the models could produce 3 circular, retrograde orbits. They consistently generated ellipses, they produced chaos, and they showed near misses, but never this exact, stable configuration. The fragments remained a confirmed yet unexplained mystery, real, but seemingly impossible. And they were not the only impossibility that Webb would uncover in this system. Stars, too, are governed by strict rules. Their temperature is directly related to their mass and age. Smaller stars burn at cooler temperatures, while larger stars burn hotter. As stars age, they typically dim, whereas young stars blaze brightly. According to all stellar models, Alpha Centauri A should have a surface temperature of 5,790 Kelvin. The laws of physics demand it. Yet Webb measured its temperature at 5,940 Kelvin, a full 150 degrees hotter than predicted. This discrepancy might sound minor, perhaps a rounding error or a matter of measurement uncertainty, but stellar models do not permit this degree of variation. Our understanding of stellar physics, from core fusion rates to radiative transfer and convection zones, is exceptionally robust. The equations work, and the predictions they generate match observations everywhere else in the galaxy. But not here. Alpha Centauri B presented the same problem. Its expected temperature was 5,260 Kelvin, but Webb's measured temperature was 5,380 Kelvin, making it 120 degrees too hot. Both stars were burning brighter and hotter than their evolutionary stage would suggest. The science team immediately checked for instrument error, wondering if Webb's sensors required recalibration. They pointed the telescope at other stars with well-established temperatures, and in every case, the readings matched perfectly. The instruments were working correctly. The data was accurate. Alpha Centauri A and B were genuinely running hot. 3 primary explanations for this anomaly emerged. The first possibility was that the stars are younger than their estimated age of 4.4 billion years. If they were, for instance, only 4 billion years old, they would naturally burn hotter, which would resolve the temperature discrepancy. However, the age estimate is derived from multiple independent methods, including analysis of stellar spectra, rotation rates, and chemical composition, all of which converge on the 4.4 billion year figure with high confidence. A second possibility involved higher metallicity. Stars containing more heavy elements burn at slightly higher temperatures because these metals increase the opacity of the outer layers, trapping heat and raising the surface temperature. But spectroscopy had measured Alpha Centauri's metal content years ago. It is 1.7 times that of our own star, and this factor is already accounted for in the models. The excess heat still could not be explained. The third possibility was an event of recent accretion, suggesting the stars might have captured new material not long ago, perhaps by swallowing comets or pulling in streams of gas from interstellar space. An influx of new fuel could offer one explanation. temporarily accelerating fusion rates and causing the surface temperature to climb. This scenario is mathematically plausible, but it relies on a continuous process of accretion, meaning the stars would need a constant supply of incoming material. The question was where such material might originate, and the debris disk orbiting Alpha Centauri A presented a possible source. This extensive field of dust circles the star within 3 astronomical units. A portion of this dust is thought to be spiraling inward over time, as the drag from stellar radiation gradually causes small particles to lose momentum and fall toward the star. It was conceivable that Alpha Centauri A was slowly consuming its own surrounding disk, an act of gradual ingestion sufficient to elevate its temperature beyond what was expected. The complication, however, was Alpha Centauri B, which also burns with unusual heat, yet showed no evidence of a similar disk when the Webb telescope searched for one. This shared characteristic suggested a common cause, something intrinsic to the system itself, rather than a phenomenon unique to one of the stars. At Princeton, Dr. Lisa Chen proposed a novel idea centered on the system's binary nature. The 2 stars are locked in a mutual orbit that brings them into a close pass every 80 years. During these encounters, immense tidal forces would stretch and stress their outer layers. This powerful friction would in turn generate heat, which would then be reflected in the temperature measurements. Mathematical models lent some support to this hypothesis, indicating that tidal heating could account for an extra 20 to 30 Kelvin. While this was not enough to resolve the entire discrepancy, it was a significant contribution. The solution likely involved multiple factors working in concert: a combination of tidal heating, some accretion, potential measurement uncertainties, and perhaps another as yet unknown process. The temperature mystery therefore persisted, a confirmed observation without a complete physical explanation, and it connected to other anomalies Webb was uncovering. Information travels across the cosmos on radio waves, which are generated by a host of natural phenomena. Pulsars emit regular radio pulses. Vast gas clouds can glow at radio wavelengths, and active galactic nuclei unleash powerful radio jets that span millions of light-years. The signal detected by the team, however, did not conform to any of these known patterns. It resembled something else entirely. In subsequent observations, scientists coordinated radio telescopes with Webb's infrared instruments, seeking a complete dataset with comprehensive coverage across multiple wavelengths. The Very Large Array in New Mexico was directed toward Alpha Centauri to collect these signals. The resulting data revealed unexpected activity in the form of a narrowband radio emission at 1,420 MHz. This specific frequency exists within a protected spectrum, reserved by astronomers for observing cold hydrogen gas in space. It is exceptionally rare for natural sources to produce such a narrow signal in this band. The bandwidth was measured at less than 1 kHz, making it incredibly precise and focused. Its point of origin was traced to the interstellar void between Proxima Centauri and the Alpha Centauri AB pair, emanating not from any star or planet but from empty space. It came from a location 13,000 astronomical units from the central binary, directly along the line connecting Proxima to its distant companions. Dr. Sofia Rodriguez at UC Berkeley was the first to notice the signal. She later explained that her initial thought was interference from Earth, noting that satellite transmissions frequently contaminate this frequency. However, the signal moved across the sky in perfect sync with Alpha Centauri, which confirmed it was not terrestrial in origin. It was real. Follow-up observations solidified the finding. The emission was present for 6 hours, then stopped, only to reappear 3 days later, indicating a distinct pattern, structure, and repetition. Formulating a natural explanation for such a signal proved difficult. Interstellar gas does not generate emissions with such a narrow band. The known physics of magnetic fields do not operate this way, and plasma instabilities typically create broadband noise, not a coherent, focused transmission. This signal was more akin to a radio transmitter carefully tuned to a single, specific channel. The research team analyzed the signal's structure, looking for any form of modulation or encoded information. They found only a simple sine wave, with no obvious patterns or messages hidden in variations of amplitude or frequency, just a clean, steady tone. The timing, however, was significant. 6 hours on, followed by 72 hours off, then another 6 hours on. These were precise intervals. Some scientists suggested the possibility of cosmic mazes, natural phenomena where molecules like water or hydroxyl radicals amplify radio waves through quantum effects, creating laser-like beams of radio light. But cosmic mazes are typically found near star-forming regions or active galactic nuclei, not in the quiet, empty space between mature stars. The location was wrong, and the mechanism remained uncertain. An alternative explanation involved planetary magnetospheres. When charged particles interact with a planet's magnetic field, they can generate radio emissions, a process observed at both Jupiter and Saturn. Perhaps a planet orbiting Proxima Centauri possessed a magnetosphere that extended far beyond the planet itself, which could then interact with the stellar wind from Alpha Centauri A and B to produce radio waves in the space between. The issue with this idea is that it would require a magnetic field of truly massive proportions, thousands of times stronger than Jupiter's. Existing planetary data gave no indication of such extraordinary strength. Proxima B has a strong field, but it is not nearly powerful enough, nor does it extend far enough, to account for the observation. The signal was ultimately classified as unidentified. Observatories worldwide added Alpha Centauri to their monitoring lists, hoping to detect more emissions and find anything that might finally crack the mystery. Meanwhile, Webb continued its observations and found something in the atmosphere of Proxima B that changed everything. Chemistry naturally seeks equilibrium. When reactive gases are mixed, they tend to destroy one another. Oxygen is a powerful oxidizer, and methane readily combusts in its presence. Given enough time, one gas or the other should be completely consumed, leaving behind stable, inert compounds like carbon dioxide and water, the signature of dead chemistry. Earth's atmosphere is a profound exception. It contains 21% oxygen and 1.8 parts per million of methane, two gases that coexist despite their reactivity. This is because life constantly replenishes them. Plants produce oxygen through photosynthesis, while bacteria produce methane in swamps and the digestive tracts of animals. This biological production outpaces chemical destruction, allowing the disequilibrium to persist. Webb's spectroscopy of Proxima B revealed the presence of both of these gases. Strong, clear signals showed oxygen absorption at 760 nanometers and methane absorption at 1,650 nanometers. The data confirmed both were present at significant concentrations, oxygen at 400 parts per million and methane at 2 parts per million, existing together simultaneously. Dr. Thomas Wright at Cambridge calculated the chemical timescales in Proxima B's atmosphere. His work indicated that the oxygen and methane should neutralize each other within a span of only 100 years. He reportedly stated that seeing them now means something must be producing them constantly. Some ongoing process is actively maintaining this chemically impossible balance. On a world without life, chemical reactions naturally move toward a state of balance. They work to resolve any disequilibrium that might exist. What the Webb telescope observed was different. It could only be sustained through some form of constant renewal. The amount of oxygen present was an especially perplexing detail for the science team. Typically, when an exoplanet has oxygen, it is a result of a process called photolysis. This occurs when ultraviolet light from a star splits water molecules apart. The lighter hydrogen then drifts away into space. This leaves the oxygen to build up in the atmosphere. The issue is that Proxima Centauri releases far less ultraviolet radiation than our own Sun. This output simply was not sufficient to produce an oxygen concentration of 400 parts per million by photolysis on its own. It became clear that another source must be involved. The creation of methane is generally tied to either organic chemistry or geological processes. Here on our own planet, we see both mechanisms at play. The vast majority of Earth's methane is a byproduct of biological activity. A smaller portion is released through geological features like volcanoes and hydrothermal vents. There is a key distinction, however. Geological methane is typically accompanied by other telltale gases. These include compounds like sulfur dioxide, carbon monoxide, and hydrogen sulfide. Yet, when Webb analyzed the spectrum of Proxima B, it found no trace of these companion gases. The data revealed only methane and oxygen, a combination of two elements that, by the laws of chemistry, should not be found together in such a state. The research team explored various non-biological chemical scenarios. They wondered if the star's ultraviolet light could be triggering strange reactions within Proxima B's atmosphere. Another possibility was that lightning strikes might be creating ozone and methane through some unconventional means. They also considered whether minerals on the planet's surface could be acting as catalysts for unexpected chemical transformations. To test these ideas, sophisticated models were developed and numerous simulations were executed. Yet none of these scenarios could naturally replicate the specific gas ratios that had been observed. The fundamental drive of chemistry is to reach equilibrium, but the conditions on this world seem to defy that principle. Only a single explanation remained on the table. It was the one conclusion that no one was yet prepared to announce in an official capacity. It was a possibility discussed in hushed tones and communicated through private messages after hours. That explanation was biology. It was the idea that living organisms were generating these gases, actively preserving the state of disequilibrium, and managing to survive within the habitable zone of our closest stellar neighbor. Of course, the presence of biosignatures does not constitute definitive proof of life. Such findings are compelling evidence that demands further, rigorous investigation. To build a stronger case, scientists required more information, additional observations, and the detection of other spectral lines corresponding to different biological markers. The discovery of phosphine, for instance, would lend significant weight to the theory. So too would the presence of ammonia or dimethyl sulfide. Any one of these gases would substantially reinforce the biological hypothesis. The Webb telescope began its search for these corroborating signals. But it instead uncovered something entirely unforeseen within the planet's transit data. When a planet passes directly between its star and our line of sight, it obstructs a small amount of the starlight. This event is known as a transit. It causes a slight, temporary dip in the star's brightness. The magnitude of this dimming allows astronomers to determine the planet's size. For example, a world the size of Jupiter will block considerably more light than a planet the size of Earth. A simple calculation can then convert this drop in brightness into the planet's diameter. It is a reliable and straightforward method, except for when it reveals a new puzzle. The transits of Proxima B produced the anticipated dimming of starlight, a 1.2% decrease in brightness. This was perfectly consistent with a planet having a mass 1.3 times that of Earth. All the initial data aligned with expectations. However, Webb's instruments registered something more in the information it gathered. There was a secondary dimming event. It was much smaller and shorter. It took place 3 hours after Proxima B had completed its own transit. This subsequent dimming persisted for 17 minutes. During that time, the star's brightness fell by just 0.03%. It was significantly less pronounced than the main planetary transit, but the signal was undeniably real. It was later verified through several independent observations. It appeared that another object was passing in front of Proxima. This object was substantial in size, and it was dark. Preliminary calculations indicated its diameter was around 1,500 kilometers. This makes it roughly the same size as Earth's moon. Yet a moon cannot maintain a stable orbit so near to a red dwarf star. The intense tidal forces would tear such a body to pieces in only a few million years. The resulting debris would spiral down into the star, or it would be flung out of the system entirely. No natural satellite could survive for long in such a close orbit. Nevertheless, the data showed that something was unmistakably there. The orbit of this mysterious object was then computed. An assumption was made that the secondary dimming was caused by a body in a circular path. Based on this, its orbital period was determined to be 2.8 days. This meant it was moving very quickly, very near to the star. It was therefore extremely hot. Any object composed of ice at this proximity would be instantly vaporized. The conclusion was that the object had to be made of rock or metal. It had to be something dense and capable of withstanding intense heat. When astronomers performed spectroscopy during its secondary transit, the results were baffling. There were no atmospheric absorption lines to be found, nor were there any signatures of reflected light. There was only the dimming effect, a pure darkness. This object seemed to absorb or block the star's light completely. It left no trace of its own features, much like a perfect shadow or a void moving through space. Dr. Rachel Foster at Yale put forward the idea that it could be a brown dwarf. Brown dwarfs are often called failed stars. They possess too much mass to be classified as planets, but not enough to ignite sustained nuclear fusion in their cores. They do emit a faint glow in the infrared spectrum from the residual heat of their formation, but they are not luminous in visible light. An object like this could account for the observed dimming without presenting any discernible spectral features. The main challenge with this hypothesis, however, was the issue of mass. The smallest brown dwarfs begin at around 13 Jupiter masses. An object of that size orbiting Proxima Centauri would exert a significant gravitational pull. This would cause the star to wobble in a very noticeable way. Such a wobble would create a large radial velocity signal, yet prior observations had revealed no such motion. This meant the enigmatic object had to be much less massive and far smaller, while still being able to obscure 0.03% of Proxima's light. An alternative explanation centered on the possibility of debris clouds. Perhaps Proxima B possesses a system of rings, and these rings happen to align edge-on from our perspective from time to time. If so, the rings would block an additional amount of starlight during the transit events. We see a similar phenomenon with Saturn in our own solar system. When Saturn's rings are perfectly aligned, they contribute to the overall depth of its transit. But the nature of a ring system is that it is spread out, which results in a gradual decrease and increase in light. The secondary event observed at Proxima had very sharp boundaries. The brightness dropped abruptly and then returned to normal just as suddenly. This light curve is not the characteristic signature of a ring system. The team continued to monitor the star, looking for additional secondary transits, and they consistently found them. Each new observation confirmed the pattern. It was exactly the same. First came the main transit of Proxima B. This was followed by a 3-hour gap. Then came the secondary dimming event, lasting 17 minutes with a depth of 0.03%. It occurred with the regularity of a clock. Whatever this object was, it behaved like a planet, with a predictable, stable, and persistent orbit. Astronomers began to refer to it as Proxima's shadow, or the dark companion, an object that, according to our understanding, should not be there, but clearly is. While scientists grappled with this enigma, a separate mystery was beginning to unfold in the vicinity of Alpha Centauri A. Brown dwarfs can be exceptionally difficult to find. Their faintness and small size make them challenging to spot, unless one conducts a careful search using powerful infrared telescopes. It was plausible that the Alpha Centauri system concealed such an object, and that it had simply gone unnoticed until this point. This raised the question of where it might be hiding, and why it had eluded detection for so long. As part of its comprehensive survey of the Alpha Centauri system, the James Webb Space Telescope conducted deep infrared scans of the space surrounding the stars. It was searching for faint companion objects, undiscovered planets, or anything else of interest. These scans concentrated on an area between 5 and 50 astronomical units from Alpha Centauri A. This particular region is generally too distant from the star for rocky planets to form. It is also too close to be easily observed from Earth-based instruments. This makes it an ideal place for an object to remain hidden. The resulting data revealed a source of infrared radiation located at a distance of 23 astronomical units from Alpha Centauri A. Its temperature was measured at 1,100 Kelvin. This was far too warm to be caused by reflected starlight, but also too cool for the object to be undergoing nuclear fusion. It was, however, the perfect temperature for either a brown dwarf that was a few million years old, or perhaps a very young, large planet, still in the process of contracting and radiating its own internal heat. The signal itself was extremely faint, only just distinguishable from the background instrument noise, but it remained consistent across several different observation periods. By analyzing the object's temperature and luminosity, scientists were able to calculate its mass. The result placed it somewhere between 4 and 8 times the mass of Jupiter, a curious position in the fuzzy boundary zone that separates planets from brown dwarfs. This location is below the accepted threshold for a brown dwarf, but above what is typically considered a planet. Because their classification is so uncertain, astronomers refer to these as planetary mass objects. The discovery process itself was a meticulous exercise in confirmation. First, the team had to ensure the signal was not merely an artifact of their instruments. Second, they needed to verify that the object was moving through space, along with Alpha Centauri, confirming their association. Third, they had to systematically rule out any background stars or distant galaxies that might be masquerading as a companion. With all of these checks successfully passed, the conclusion was firm. The object was a genuine member of the system, in orbit around Alpha Centauri A. This presented a curious puzzle, however. An object of this significant mass should have been detected years ago in the numerous radial velocity surveys conducted on the star. Alpha Centauri has been a subject of intense study for decades, with high-precision spectrographs measuring its subtle movements in search of orbiting companions. Yet, nothing this massive ever appeared in the data. The question was why it had remained unseen. One compelling possibility involves its orbital inclination. The radial velocity method can only detect motion that is directed toward or away from Earth. If an object's orbit happens to be oriented perpendicular to our line of sight, its radial velocity signature drops to 0. Under such conditions, we would never see it using that technique, no matter how large it was. The Webb telescope, however, sees it directly. Its ability to detect the object's infrared glow, its faint heat signature, is not dependent on orbital angles or its motion relative to us. Another potential explanation lies in its vast and lengthy orbit. At a distance of 23 astronomical units from Alpha Centauri A, its orbital period is estimated to be around 80 years. Previous observational campaigns had covered a maximum of 15 years, a window of time simply too short to register a complete orbit. There was not enough data to discern the slow, patient gravitational influence of such a distant companion. The object effectively stayed hidden by moving slowly, cycling through its long year while humanity watched for much faster signals. The team went on to calculate the possibility of future transits. They considered whether this object might one day pass in front of Alpha Centauri A as seen from Earth. The chances are likely very low, as orbital inclinations rarely align so perfectly. Still, such an event might occur once every few thousand years. It's possible that ancient astronomers witnessed Alpha Centauri dim slightly and simply dismissed the observation as an error in their measurements. Perhaps we will see it transit 300 years from now, or perhaps we never will. The presence of this object complicates the system's dynamics, which now consists of 4 stellar or substellar masses. There is Alpha Centauri A, Alpha Centauri B, Proxima Centauri, and this newly found companion. That makes 4 distinct gravitational sources, all pulling on one another, creating a complex web of resonances and perturbations. At first glance, the system might appear crowded, even chaotic, and yet, the remarkable fact is that it has remained stable for billions of years. A deeper stability analysis revealed the reason for this harmony. The new object travels in an orbital plane that is different from that of the main binary stars. This 3-dimensional separation is key, as it prevents close encounters and the gravitational chaos that would otherwise ensue. Everything moves through space in a delicate balance, without collision or disruption. The system is harmonious despite its complexity. This brown dwarf, or planetary mass object, also raised an intriguing question. If one large companion could remain hidden in the system for so long, perhaps others could as well. The light that bounces off a surface tells a story about its composition. A rough, rocky surface scatters light in every direction, while smooth water can reflect it like a mirror. Ice tends to glitter, and metal gives off a distinct gleam. By reading the spectrum of this reflected light, you can begin to read the surface itself. The Webb telescope captured this kind of reflected light from Proxima B during its orbit, not during a transit. It observed the planet during the phases when it reflects Proxima's red starlight back toward Earth, much like our moon reflects sunlight or how we see the phases of Venus. As the planet orbits, it reveals different amounts of its dayside, and each phase provides more information about its surface. The resulting reflection spectrum showed a particularly distinctive feature. There was a sharp increase in the amount of reflected light at specific wavelengths, between 600 and 750 nanometers. This specific pattern is a strong match for liquid water. More precisely, it matches the glint of starlight reflecting off the surface of an ocean. This effect, known as specular reflection, is constantly seen on Earth by satellites, where the crests of waves catch sunlight at the perfect angle. Dr. Amy Liu at Johns Hopkins, who analyzed the data, reportedly described it as the clearest signature of an ocean that we have ever seen on an exoplanet. The reflection pattern, its dependence on wavelength, and its polarization all seem to point toward liquid water covering a significant portion of the planet's surface. Her team calculated that somewhere between 30 and 70% of the planet's dayside exhibits this distinctive water glint, providing strong evidence for an ocean world. But the presence of water on a tidally locked planet creates a theoretical problem. The dayside is locked in a state of constant baking under the star. Any water there should evaporate, rise into the atmosphere, and then freeze solid on the perpetually dark night side. Over time, this process should trap all the planet's water as ice on the cold hemisphere, leaving the dayside completely dry. This is what models have long predicted. Reality, however, showed something different. Proxima B has somehow maintained liquid water on its dayside. The ocean does not evaporate completely. This implies that water must be cycling back from the night side, allowing the system to reach a stable equilibrium. The result is an ocean on the dayside and a vast sheet of ice on the night side, connected by a system of atmospheric transport. This is a hydrological cycle that spans an entire planet. The terminator zone, the boundary between day and night, is likely where most of the water activity occurs. Here, temperatures remain moderate, allowing water to exist as both liquid and ice at the same time. This is also where weather systems would form. Storms develop along the terminator as wind carries moisture from the warm dayside. This moisture then falls as precipitation rain on the dayside and snow on the night side, continuing the cycle. Webb detected evidence of these very weather patterns. It observed temperature variations along the terminator and saw cloud formations in the infrared. The data suggested convection cells rising from the warm ocean and cold fronts descending from the frigid night side. The atmospheric dynamics seem to match the basic weather processes on Earth, though they are organized in a different way. Instead of cyclonic patterns, Proxima B appears to have linear storms that stretch along the terminator, a result of different physics driving the same fundamental processes. The conformation of liquid water elevated Proxima B from a world that was potentially habitable to one that is actually habitable. Liquid water means that chemistry can happen, that complex organic molecules can form. It raises the possibility that life could emerge, or perhaps that it already has. All of the pieces seem to fit together. A protective magnetic field, a stable atmosphere, liquid water, and the potential for disequilibrium chemistry. Every indicator pointed toward a profound conclusion, but scientists do not declare the existence of life based on indicators alone. They require definitive proof, unambiguous biosignatures, and evidence that can withstand the rigors of peer review and skeptical scrutiny. The atmospheric data provided important clues, and the reflection spectra offered critical context. What would come next would be the search for definitive answers. The existence of seasons on a planet requires an axial tilt. Earth, for instance, tilts at 23.5 degrees. This tilt is what causes our seasons, as one hemisphere leans toward the star during its summer. On Earth, seasons are a product of our planet's axial tilt, a simple consequence of geometry as we lean toward or away from the sunday. The exoplanet Proxima B, however, is tidally locked, with one hemisphere perpetually facing its star. In such a configuration, an axial tilt becomes irrelevant, and the very concept of seasons should be non-existent. And yet, the James Webb Space Telescope detected clear seasonal changes. Over a continuous 3-month observation period, a distinct pattern of temperature shifts emerged. The planet's dayside experienced a cooling of 12 Kelvin across those 90 days, while the night side, in contrast, warmed by 8 Kelvin. The most pronounced transformation occurred along the terminator zone, the twilight region between day and night. Here, atmospheric pressure saw a notable increase of 15%, and at certain latitudes, wind speeds actually doubled. It was clear that something cyclical was altering the planet's climate. Dr. Marcus Flynn of MIT offered a compelling explanation, suggesting the cause was the planet's orbital eccentricity. Even a slight deviation from a perfect circle can create significant variations in distance between a planet and its star. Proxima B, it turns out, follows a mildly elliptical path, moving closer to and then farther from its red dwarf. This change in proximity directly alters the amount of stellar radiation the surface receives, causing temperatures to rise and fall. These are seasons driven not by planetary tilt, but by the elegant mechanics of its orbit. The science team calculated Proxima B's orbital eccentricity to be 0.08, a small figure with profound implications. At its closest point, or perihelion, the planet is just 7 million kilometers from Proxima Centauri. At its farthest, or aphelion, that distance increases to 8.2 million kilometers. This difference of 1.2 million kilometers is enough to vary the incoming stellar radiation by a remarkable 30%, more than sufficient to drive significant weather changes and create a seasonal cycle. These seasons, however, operate on a much faster timescale than Earth's, unfolding over a brief 11-day cycle. Each orbit brings a complete transition from summer to winter. For any life that might exist there, this would mean contending with constant environmental flux. Adaptations would have to favor flexibility and resilience, demanding biological mechanisms capable of handling dramatic temperature swings every week and a half. The Webb telescope also observed the response of the planet's global ocean to this cycle. As Proxima B neared its star, increased evaporation sent vast amounts of water vapor into the atmosphere. This led to the formation of extensive clouds across the dayside, which in turn increased the planet's albedo, reflecting more sunlight back into space. It was a natural thermostat, a system seemingly protecting the world from overheating. Conversely, as the planet moved away from its star, evaporation slowed and the cloud cover dissipated. With fewer clouds, the ocean could absorb more starlight, allowing temperatures to stabilize. This reduction in albedo meant more heat reached the surface, acting as another thermostat but in reverse, warming the planet during its cooler phases. This intricate feedback system hinted at sophisticated atmospheric dynamics, not chaotic fluctuations, but an organized response to orbital forcing. The planet was behaving like a self-regulating system, something seemingly engineered to maintain stability against external pressures. The seasonal cycle's influence extended beyond just temperature. It also caused shifts in the atmospheric chemistry. Concentrations of oxygen were observed to peak when the planet was closest to its star and then drop during the more distant phases of its orbit. Methane exhibited the opposite pattern, becoming scarce at perihelion and more abundant at aphelion. The fact that these gases varied with the seasons, responding to changes in temperature and radiation, was intriguing. It was a pattern that strengthened the hypothesis of a biological origin. While chemical reaction rates are influenced by temperature, they typically do not fluctuate by factors of 2 or 3 with such a perfect correlation to orbital position. Biological systems, on the other hand, often respond dramatically to environmental cues, with metabolic rates and production cycles varying in precisely the way the data indicated. But these seasonal discoveries were not the most unsettling find that Webb made. That revelation came from an entirely different and unexpected direction. Gamma-ray bursts are counted among the most cataclysmic events known in the universe, occurring when massive stars collapse into black holes or when neutron stars collide. In these moments, matter is torn apart by unimaginable gravity and accelerated to nearly the speed of light. The resulting pulse of radiation can briefly outshine entire galaxies before vanishing forever. On March 17, 2024, NASA's Fermi Gamma-ray Space Telescope registered such an event. It lasted for 2 seconds and had an energy signature consistent with a short gamma-ray burst. The direction of its origin was Alpha Centauri. This was a profound anomaly, as gamma-ray bursts are phenomena of deep space, originating in distant galaxies billions of light-years away. Discovering one at a mere 4 light-years from Earth seemed to violate all probability and everything understood about their origins. The alert triggered an immediate, worldwide response. Observatories across the globe pivoted their instruments toward Alpha Centauri. The James Webb Space Telescope interrupted its scheduled observations. Radio telescopes began searching for an afterglow, and optical telescopes looked for any sign of an associated supernova. The scientific community was searching for a source, all while expecting to find nothing, because a local burst of this nature simply should not be possible. Preliminary analysis revealed another strange detail. The burst had not originated from Proxima Centauri itself, but from a point behind it, as seen from Earth. It came from the empty space between Proxima and the Alpha Centauri binary stars, the very same region where the mysterious radio signal had been detected months before. It was the same location, but an entirely different phenomenon. Dr. Kevin Zhang at Caltech, upon examining the burst's energy spectrum, reported that it did not match any known gamma-ray burst profile. He noted it was too low in energy for a stellar collapse, too brief for magnetar activity, and too structured for random particle acceleration. The event displayed 3 distinct peaks, not the single smooth pulse characteristic of normal bursts. These 3 separate energy releases within 4 seconds had a patterned, almost artificial quality. Webb's infrared instruments captured data during and after the burst, searching for any heat signature, expanding debris cloud, or other evidence of an explosion or collision. Nothing appeared. The region remained dark, empty, and unchanged. Whatever had generated the gamma-ray burst left no visible aftermath. no glowing remnant, and no expanding shockwave. There was only the burst itself, and then an unnerving silence. Due to the geometry of the solar systems, the radiation from this event reached Proxima B approximately 25 seconds after it was detected at Earth. As the wave of energy struck the planet, Webb watched its atmospheric response, anticipating ionization, disruption, and widespread damage. Instead, the atmosphere absorbed the burst. While the upper layers heated rapidly and electrons were scattered, conditions normalized within minutes. The planet's magnetic field had deflected the majority of the high-energy particles, and its thick atmosphere absorbed the rest. The world had survived the blast without catastrophic harm, proving itself to be resilient, protected, or perhaps just incredibly lucky. The scientific community began to debate the burst's origin, as natural causes seemed increasingly unlikely. The location appeared wrong, the energy profile was incorrect, and the structure was anomalous. Yet an artificial origin seemed impossible. The immense power required for gamma-ray bursts is typically associated with the collapse of a star. No known technology is capable of producing such an event. It is difficult to imagine any form of engineering that could generate directed gamma radiation on this scale. Of course, this assumes our current engineering concepts are not profoundly limited. It assumes nothing exists beyond our present framework of understanding. A disquieting alternative was that the burst was not an accident of nature, but a signal. Perhaps it was a message, or even a demonstration of technological capability. This line of thinking created a sense of unease. It prompted researchers to re-examine their own observations. It led to demands for repeated and rigorous verification. Subsequent observations of the same region of space, however, detected nothing. The burst was a singular event. It never happened again. It left behind only questions instead of answers. It offered mysteries in place of solutions. While scientists grappled with the puzzle of the impossible gamma rays, another unsettling pattern began to emerge from Proxima's own behavior. The star is known to erupt with flares that occur without any warning. These events are born when magnetic field lines become tangled within the star's outer layers. Eventually, they snap. Then, they violently reconnect. This sudden reorganization releases a tremendous amount of energy. A flood of radiation travels outward at the speed of light. Charged particles follow just minutes behind. Any object in the vicinity is struck. It is burned. It is bombarded by lethal doses of X-rays and ultraviolet light. Proxima erupts with considerable frequency. A new flare explodes from its surface every few weeks. These are mostly medium-strength Class M flares. Occasionally, however, an extreme-strength Class X event occurs. Such flares can increase the star's brightness by 10 to 25%. They typically last for a period of minutes to hours. During these outbursts, they bathe Proxima B in levels of radiation that would sterilize the surface of Earth in mere seconds. The Webb telescope documented 12 separate flares over an 8-month period of observation. Each one of these events was captured in remarkable detail. Each was measured across a wide range of wavelengths. Each one was tracked as its effects reached Proxima B. The resulting data revealed a story of both destruction and adaptation. It was a narrative of both profound danger and incredible survival. During a Class X flare that occurred in June 2024, radiation struck Proxima B with an intensity of 700 watts per square meter. For the sake of comparison, Earth normally receives 1,360 watts per square meter from our own Sunday. The critical difference was that this energy was concentrated in X-rays and extreme ultraviolet bands. This was ionizing radiation. It was DNA-destroying radiation. It was life-ending radiation. Proxima B's magnetic field showed an immediate response. The field lines compressed on the planet's day side. They stretched out on its night side. This process formed a protective bubble. The magnetosphere was morphing under the immense pressure. It channeled the dangerous particles toward the poles. This, in turn, created auroras that were visible to Webb's infrared sensors. The sensors detected green and red light from atmospheric oxygen being struck by the charged particles. The planet's entire day side was glowing, its atmosphere heated with incredible speed. The temperature in the upper layers leaped from 300 Kelvin to 600 Kelvin in just a few minutes. Atmospheric molecules began to dissociate. Water vapor was broken apart into hydrogen and oxygen. Carbon dioxide was split into carbon monoxide and atomic oxygen. The planet's chemistry was thrown into chaos by the radiological assault. The atmosphere was fighting for its own survival, and it did survive. The lower atmosphere remained shielded from the worst of the event. Conditions at the surface stayed stable. The temperature of any oceans barely changed. If anything lived down there, it remained protected by the mass of the atmosphere and the deflection of the magnetic field. The flare eventually passed. The aurora faded from view. The atmospheric chemistry began to reassemble itself. Molecules started to reform. Within hours, spectroscopy showed that the atmosphere's composition had returned to normal. Water vapor levels were restored. Oxygen concentrations stabilized. The planet was healing itself. This same pattern repeated with every single flare. There was an attack, then a defense, then a recovery. Attack, defense, recovery. This cycle was observed 12 times. It has likely occurred thousands of times over billions of years. The planet seems to have developed its own mechanisms. It has evolved specific responses. It has learned to survive its violent host star through the interplay of its atmospheric chemistry and its magnetic protection. Dr. Patricia Moore at Oxford calculated just how many such flares Proxima B has likely endured over its lifetime. The number is approximately 10 million. That is 10 million individual radiation bombardments. It represents 10 million moments where life could have been extinguished. It is 10 million separate tests of the planet's resilience. And with each test, the planet passes. It absorbs each blow. It continues to exist despite the violence raging overhead. This survival, in itself, became a form of evidence. Natural processes could certainly create a protective magnetic field. They could also create a thick atmosphere. But surviving 10 million flares seems to require something more. It suggests a process of adaptation. It implies the existence of complex feedback systems that maintain atmospheric composition. It points to repair mechanisms that work faster than the rate of damage accumulation. On our own world, life developed repair enzymes for DNA damage. It evolved antioxidants for radiation protection. It created states of dormancy to survive extreme conditions. If life does exist on Proxima B, it must have developed similar mechanisms. It would have needed to evolve even more sophisticated protections given its hostile environment. It would have to be tougher, more resilient, and more adapted than anything found on Earth. Yet, toughness alone cannot explain what Webb discovered next. The finding came from temperature data focused on the terminator zone. The terminator is a line that circles the entire planet. It is a ring of perpetual twilight. It is a region of neither full day nor complete night, but the boundary between them. Here, the star sits forever upon the horizon. It never truly rises, and it never truly sets. It is a frozen sunset, stretching around the world's full circumference. This makes it the most stable region on a tidally locked world. The temperature in the terminator zone holds steady at 270 Kelvin. By older temperature scales, that is 3 degrees below the freezing point of water. Liquid water can exist there, however, because the atmospheric pressure and dissolved salts lower its freezing point. This could create slushy oceans or mixtures of ice and water. It is a perfect environment for complex chemistry to unfold. It provides the perfect conditions for life to emerge. If it were to emerge anywhere, Webb mapped the terminator with an unprecedented level of detail. The resolution was 20 kilometers. This was clear enough to see variations in temperature. It was clear enough to detect localized hotspots. It was clear enough to find something that no one had anticipated. The data revealed an organized structure. The hotspots were found at regular intervals. They appeared every 250 kilometers all the way around the terminator. There were 30 of these spots in total. Each one measured 5 Kelvin warmer than its immediate surroundings. Each one was circular in shape. Each had a diameter of approximately 50 kilometers. The pattern was too regular to be explained by geology. It was too organized to be the result of weather patterns. It seemed too perfect to be the product of random natural processes. Dr. Hannah Lee at Stanford analyzed the distribution of these features. She noted that the hotspots appeared to form a grid. It was not a random scattering of points, but a deliberate pattern. She remarked that it was similar to how cities on Earth might appear when viewed from space at night. They were heat islands, spaced evenly along the most optimal habitable zone. This comparison made everyone feel uncomfortable. Cities imply intelligence. They imply construction. They imply a conclusion that nobody was ready to accept without absolute proof. The search for alternative explanations began immediately. While volcanic activity could theoretically generate hotspots, a key inconsistency arose from the data. Volcanoes tend to form in clusters, typically following the boundaries of tectonic plates, rather than distributing themselves uniformly across a surface. The thermal features on Proxima B, however, displayed none of this characteristic grouping. Hydrothermal vents, another potential explanation involving underwater heat sources, were also considered, but these vents generally appear in random locations, not in organized grids or circular formations. A different natural process, atmospheric convection, can create patterns of heat as warm air rises and cooler air descends, forming cells across the planet's terminator line. Yet, convection cells are inherently unstable. They drift, merge with one another, and split apart over time. In stark contrast, these particular hotspots remained completely fixed in place, their positions unchanging month after month through every single observation. Their immobility was a profound mystery. The infrared signature provided further clues, revealing an internal structure to these areas of warmth. The center of each spot was the warmest, with the temperature gradually decreasing toward the edges, a pattern consistent with heat radiating from a distinct point source. This suggested something was actively generating warmth from within or below the surface, rather than the heat being a result of absorbed starlight or simple solar heating. Scientists were able to calculate the energy output of these features. Each individual hotspot was found to radiate approximately 1 megawatt of power, with a total of 30 spots. This amounted to a combined output of 30 megawatts. While this is not an enormous amount by planetary standards, Earth's geothermal output, for instance, reaches 44 trillion W. The energy on Proxima B was concentrated in very precise locations and arranged in what appeared to be perfect patterns. The very nature of this energy distribution hinted at something more than natural processes. It suggested a deliberate design, as if something had chosen exactly where to place these sources of heat. The research team rigorously searched for any possible correlations. They investigated whether the hot spots aligned with magnetic field patterns, but found no connection. They checked for a relationship with ocean currents, but again, there was none. The possibility that they marked significant geological features could not be ruled out, but it also could not be confirmed. Proxima B's surface remained completely hidden beneath its thick atmosphere, as the Webb telescope is designed to see heat and atmospheric composition, not topography or fine surface details. The hotspots could be marking anything, and their meaning remained elusive. As news of the discovery spread, public pressure began to build for an interpretation of the findings. News outlets pressed for explanations, and social media platforms became flooded with speculation. The scientists involved resisted the urge to jump to conclusions. remaining cautious about suggesting intelligence without first conducting an exhaustive analysis. They fought against the obvious interpretation that seemed to be staring back at them from the data. But such resistance is only sustainable when viable alternatives exist, when other natural explanations can adequately fit the observations. In this case, none did. It seemed that nothing fit the evidence, except for the one explanation that nobody was willing to state publicly. The hotspots were officially classified as anomalous thermal features, their existence confirmed but their origin unexplained, making them real yet deeply mysterious. And remarkably, they were not the most controversial discovery the Webb telescope made on Proxima B. The presence of phosphine gas in an atmosphere rich with oxygen is a chemical paradox. These two gases react with each other quite violently. Phosphine rapidly oxidizes, breaking down into phosphates and disappearing from the atmosphere within a matter of hours or days. Therefore, finding phosphine and oxygen coexisting implies that something must be continuously producing phosphine, requiring a constant and active chemical process. On our own planet, the only known processes that produce enough phosphine to maintain a concentration in the atmosphere are biological. This includes anaerobic bacteria in swamps and microbes found in the intestines of animals. In essence, life creates phosphine at a rate faster than chemistry can destroy it. The Webb telescope detected phosphine on Proxima B. It was not a mere trace amount or a barely detectable wisp. The data showed a strong signal of 20 parts per billion, with clear spectral lines at a 3,000 micrometers wavelength. This finding was confirmed across 6 separate observation sessions. The impossible chemistry of coexisting phosphine and oxygen was a reality. In an effort to find a non-biological source, Dr. Samuel Brooks at Yale University ran every available abiotic model. He explored whether lightning could create it, if volcanic gases could carry it, or if photochemical reactions might generate it. The models did produce some phosphine, but only up to a maximum concentration of 0.5 parts per billion. This was far below what was observed, creating a 40-fold gap between the models and the actual data. Chemistry could not account for it, geology could not explain it, and physics offered no solution. As the team delved deeper, they found more. Dimethyl sulfide, another gas primarily produced by marine phytoplankton on Earth, was also present in Proxima B's atmosphere at a concentration of 5 parts per billion. This was yet another gas that lacked known abiotic production mechanisms, another potential biosignature. Then, methyl chloride appeared in the data at 7 parts per billion. On Earth, this gas is associated with tropical plants, coastal algae, salt marshes, and seaweed, all forms of life that process chlorine and organic compounds. Finding it around a star 4 light-years away suggested processes that were strikingly similar to Earth's biology, hinting at the presence of life and entire ecosystems. There were now 3 distinct biosignature gases, and while each one was suggestive on its own, their combined presence formed a compelling pattern. It was a metabolic pattern, the signature of biological activity cycling elements like carbon, sulfur, phosphorus, and chlorine through organisms and back into the atmosphere. These elements were all being processed, released as gases, and appearing in concentrations that strongly pointed toward biology. Scientists were able to construct scenarios where non-biological processes might explain one biosignature, or perhaps even 2. But for all 3 to appear simultaneously, and all in concentrations 50 to 100 times higher than any abiotic model could predict, the probability dropped to less than 1 in 10 million. While not strictly impossible, such an extraordinary claim of a non-biological origin would require equally extraordinary evidence. The metabolic ratios of the gases also held significance. On Earth, the ratio of oxygen to methane to phosphine follows predictable patterns determined by biological productivity. Although these ratios are affected by seasonal changes, the underlying relationships remain constant. Proxima B's atmosphere showed similar ratios. They were not identical matches to Earth's, but they were close enough to suggest similar biological processes, similar metabolisms, similar life. Critics argued for the possibility of unknown chemistry, pointing out that our understanding of exoplanet atmospheres is far from complete. They suggested that new chemical processes and reactions we have yet to discover might exist. This was a valid criticism and an important expression of scientific skepticism, which the process demands. However, such demands can become excuses when the data continues to accumulate, with every new observation strengthening one interpretation while weakening the alternatives. The debate over the biosignatures intensified throughout 2024. Scientific conferences dedicated entire sessions to Proxima B, and journals were flooded with papers on the subject. Everyone seemed to have an opinion and wanted their interpretation to be accepted, but the data itself remained stubborn, consistent, and increasingly difficult to explain without invoking the presence of life. Then, in August, during a series of routine transit observations, the Webb telescope detected something that made the biosignature debate seem almost trivial by comparison. A planet's transit across its star follows a predictable curve. The star's light dims gradually as the planet begins to move across its disk, reaches a minimum brightness during the full transit, and then gradually brightens again as the planet exits. The result is a smooth, mathematically perfect curve unless something interrupts the transit, unless something else is blocking the star's light, and unless the planet is not alone. On August 12th, the James Webb Space Telescope fixed its gaze on Proxima B as the exoplanet began its anticipated 2-hour transit across its star. For the first 40 minutes, everything proceeded as expected, with the star's brightness dipping in a smooth, predictable curve. Then, an anomaly occurred. The light did not return to its baseline, nor did it remain at the full dimness of the transit. Instead, it suddenly spiked, recovering not to its normal level but to 98% of the star's usual brightness, where it held steady for 2 minutes. After this brief interruption, the light dropped once more to the full depth of the transit. A second, similar spike appeared at the 83-minute mark, another 2-minute departure from the norm. Following this event, the transit concluded without further incident. At Caltech, Dr. Jennifer Walsh immediately began her examination of the perplexing data. Her initial thought, she later relayed, was that the telescope had been struck by a cosmic ray. Yet, what she observed was not random noise. The spikes themselves possessed a clear structure. They had distinct shapes and measurable durations. When Dr. Walsh overlaid the data from 6 separate transit observations, the peculiarity of the August 12th event became undeniable. 5 of the observations showed the smooth, graceful curves of an uninterrupted transit. Only one displayed the 2 symmetrical spikes, identical in their magnitude, duration, and placement within the planet's passage. This was not an instrument error. It was a real variation in the light curve. The team set to work calculating what could possibly create such specific signatures. Their models pointed to something smaller than Proxima B itself, an object either orbiting the planet or accompanying it. This object would have to be blocking less light than the planet, allowing for the brief recovery of brightness. Ring systems can produce similar effects, but there is no evidence that Proxima B has any. The investigation turned to another possibility, something massive in orbit around the planet. The principles of orbital mechanics offered a potential explanation. 2 objects, orbiting Proxima B at different distances from its center, could be the cause. As the planet crosses the star, these objects could move in and out of our line of sight, briefly unblocking a fraction of the star's light and creating the spikes. In other words, they could be natural satellites or moons. The problem with this theory is that tidal forces from a red dwarf star should prevent moons from maintaining such a close orbit. An alternative calculation suggested objects located in stable Lagrange points, These are areas of gravitational equilibrium where objects can orbit in lockstep with a planet, maintaining a fixed position relative to both the planet and its star. Earth's own Lagrange points are known to collect dust and asteroids. Jupiter's Lagrange points have famously captured the Trojan asteroids. It was conceivable that Proxima B's Lagrange points contained large objects that occasionally crossed our line of sight. However, objects in Lagrange points typically do not create symmetrical spikes or appear at such predictable intervals. The precision seen in the August 12th data did not fit this model. The symmetry of the event was what troubled everyone most. Nature tends toward asymmetry, chaos, and random distributions. Such perfect symmetry hints at a deliberate arrangement, suggesting intention and even design. It was this observation that led Dr. Walsh to propose an uncomfortable hypothesis. In private conversations, late-night emails, and notes scribbled in the margins of conference papers, she began to wonder if the objects were not natural. What if, she asked her colleagues, we are seeing structures that something has built? What if they were placed in orbit around the planet for a specific purpose? What if these are artifacts? This idea was immediately met with resistance from senior scientists, who insisted that more data was needed. They argued that a single anomalous transit proved nothing. The spikes could be caused by dust clouds, a subtle instrument artifact, or any number of other unknown phenomena. These were valid criticisms, yet a deep suspicion lingered. The spikes appeared exactly where one might strategically place structures in orbit around a habitable world, positioned to maximize some unknown advantage. They seemed placed, arranged, and intentional. Follow-up observations were scheduled to monitor more transits. The September and October passes showed nothing unusual. November, December, and January all produced normal transits with smooth, predictable curves. Then, on February 8th, the anomaly returned. Two spikes appeared again, with the same magnitude and duration as before. This time, however, they were in different positions within the transit's timeline. They were not random, and they had not disappeared. They were still there, suggesting something organized was orbiting the planet. Even in private, scientists stopped using the word artificial, finding it too controversial and explosive. They adopted neutral, safer language, referring to the events as orbital anomalies. This terminology avoided triggering sensational headlines or jeopardizing funding reviews. But everyone understood what the anomalies implied. Everyone avoided saying it aloud. Everyone simply waited for more data to force the conversation into the open. That data eventually arrived, but from a different source. It came not from Webb, but from Earth, and it addressed the one question that nobody wanted to ask, but that everyone needed answered. The distance of 4.37 light-years is equivalent to 25 trillion miles. For a person walking, the journey would take 80 million years. Even with our current spacecraft, it would require 70,000 years. The distance seems vast and unbridgeable with existing technology. Yet, on a cosmic scale, Proxima Centauri is in our immediate neighborhood, practically in our front yard. It is close enough to matter, close enough to someday reach, and close enough to change everything. The accumulated evidence suggesting life exists there was becoming overwhelming. Science rarely proves anything with absolute certainty. Instead, it builds a case by gathering evidence until a certain threshold of confidence is reached. For Proxima B, that threshold kept rising. The atmosphere contained both oxygen and methane existing together. There were impossible concentrations of phosphine, along with dimethyl sulfide and methyl chloride. Data pointed to the existence of surface oceans, a protective magnetic field, and a stable climate. One biosignature after another was piling up. In December 2024, Dr. Robert Chen at Harvard compiled a comprehensive analysis. He calculated the probability of these findings, starting with a conservative assumption that each individual biosignature had a 90% chance of having a non-biological or abiotic origin. The probability of all 5 of these biosignatures appearing together through purely abiotic processes was calculated to be 0.59%. This meant there was a less than 1% chance they were a coincidence. The conclusion was a statistical argument, not absolute proof, but it was incredibly compelling. It suggested a greater than 99% chance of a biological origin. The implications of this analysis sent ripples through the scientific community and far beyond. If life exists just 4 light-years away, the probability of life elsewhere in the cosmos skyrockets. The universe contains an estimated 200 billion trillion stars. If our very nearest neighbor hosts life, then the cosmos must be filled with it. It would be filled with biology, with chemistry that has grown complex, and with the answer to humanity's oldest question, are we alone? Responses from religious communities were varied. Some saw the discovery as a confirmation of a divine creation that extended beyond Earth. Others struggled with the theological implications. Many celebrated a scientific discovery that forced philosophical adaptation, new interpretations, and profound growth. Quietly, political discussions began to take shape. If life exists at Proxima, should we attempt to send messages? Should we try to make contact? Should we begin preparations for future missions? Governments formed committees, which in turn formed subcommittees, all debating scenarios for a future where life either did or did not exist beyond our world. The public conversation, meanwhile, exploded across social media. Millions of people shared their opinions, demanded answers, and wanted immediate confirmation or denial. Scientists found themselves trying to explain the nature of uncertainty, communicating the nuances of probabilistic thinking, and teaching the world why being 99% confident is not the same as being absolutely certain. The discovery was at odds with the deep-seated human desire for certainty. In response, space agencies around the world began outlining missions to journey to Proxima B. Their goals were straightforward: to achieve closer observations, take direct measurements, and ultimately confirm or refute the presence of biosignatures. NASA proposed a flyby mission that would utilize solar sail technology with a projected launch in 2030 for an arrival in 2070, marking a 40-year transit. The European Space Agency put forth a faster alternative involving a laser-pushed light sail, which would launch in 2035 and reach its destination in 2055, a journey of only 20 years. Though ambitious and expensive, the concept was considered possible. China also announced its own program, but its details, timeline, and capabilities remained classified. A competitive spirit, reminiscent of an earlier space race, began to surface with this new contest driving technological innovation. The very possibility of confirming extraterrestrial life was acting as a powerful accelerator for technological progress. The challenge, however, was one of immediacy, as missions launching decades in the future could not resolve the urgent questions of the present. They did not satisfy the intense curiosity of the moment or settle the debates already underway. Scientists required more from the instruments they already had. They needed the Webb telescope to find something definitive, a piece of evidence so strong it could not be denied. They sought the one observation that would put an end to all speculation. That observation did arrive, though not in the way anyone had foreseen. Normally, emergency observation time is not available for the James Webb Space Telescope, which operates on a meticulously planned schedule. Every single hour is allocated months in advance through a competitive process involving hundreds of proposals, review committees, and strict procedures. Yet, the rules allow for exceptions in extraordinary circumstances, such as a supernova, an asteroid impact, or any discovery that demands immediate follow-up. In February 2025, Proxima B became one of those extraordinary discoveries. The trigger, however, was not Webb or any optical instrument. It came from radio telescopes. The Very Large Array detected a signal originating from Proxima B during its transit observations. It was a narrow-band emission at 1,420 MHz, a protected frequency. This was the same frequency that had been detected months earlier between Proxima and the Alpha Centauri binary system, but this new signal was stronger, more structured, and seemingly more deliberate. The transmission lasted for 6 minutes, beginning precisely as the planet started its transit and ceasing the moment the transit concluded. The timing made coincidence seem highly improbable. The statistical probability of a random radio emission starting exactly within that 2-hour transit window was a mere 0.3%. This was a low and suspicious figure, one that warranted a thorough investigation. The radio astronomy team issued urgent alerts, and an emergency request for Webb's time was granted, redirecting the telescope's observations within just 8 hours. At the SETI Institute, Dr. Sarah Martinez analyzed the signal's structure. She reported that it was not consistent with plasma noise or interactions within a magnetosphere. Instead, her analysis showed clear modulation, frequency shifts, and a distinct pattern. This pattern repeated itself every 30 seconds, featuring a rise in frequency, a flat section, a drop in frequency, and another flat section, much like a carrier wave embedded with information. Efforts to decode the transmission began immediately. The signal did not conform to any known communication protocols and bore no resemblance to human radio engineering. Nevertheless, it contained a clear structure and organization, something that looked like data being sent by someone attempting to communicate. This interpretation deeply divided the scientific community. One camp advocated for natural explanations, suggesting phenomena like atmospheric plasma oscillations, massive lightning discharges, or molecular masers, all of which are known to produce radio emissions and can create structured signals. However, none of these natural sources could perfectly match the observed pattern, explain its precise timing, or account for its frequency precision. The other camp saw clear intention, viewing the transmission as a deliberate signal and a possible attempt at communication. They argued for an immediate response, advocating for sending radio messages back toward Proxima to engage with whatever intelligence might be there. The first group condemned this as premature and dangerous, a violation of established protocols for extraterrestrial contact. The debate quickly intensified, spilling over into political and even personal arenas. Webb's emergency observations were aimed at Proxima B's atmosphere during its next 5 transits. Scientists were searching for simultaneous infrared anomalies or any atmospheric changes that correlated with the radio signals, hoping to find anything that could either explain or confirm the signal's origin. Then, March brought another detection. It was on the same frequency and had the same pattern, but its duration was different, lasting 8 minutes instead of 6. In all other respects, it was identical. The pattern appeared to hold informational content. A computer analysis measuring its Shannon entropy revealed that the signal contained 2.4 bits per symbol. This was far from random noise or a simple oscillation. It was complex enough to encode information, yet simple enough that it could still be a natural process. The signal existed on the ambiguous boundary where the natural and the artificial become blurred. In response, international committees were formed to discuss protocols for how to proceed. The United Nations Office for Outer Space Affairs became involved, sparking a global debate over whether humanity should reply to unconfirmed signals. The discussion expanded to who would speak for Earth and how to balance the immense risks against the potential opportunities. All the while, the signals continued to appear. Through March, April, and May, each transit of Proxima B was accompanied by radio emissions. Each emission was slightly different, suggesting communication without ever proving it. Scientists pushed for more observation time and continuous monitoring, urging that every available instrument be pointed at Proxima whenever possible. The signals represented either an extraordinary natural phenomenon or the first contact with an alien intelligence. Either possibility demanded maximum effort, resources, and attention. The debates raged on through the summer of 2025 with no consensus, no agreed-upon protocol, and no decision on a response. There was only observation, data collection, and the steady accumulation of information that refused to resolve into a clear answer. And as humanity debated its next move, the implications of what had been found forced a confrontation with what could come next. At a distance of 37 light-years, where one astronomical unit is 93 million miles and 1 light-year is nearly 6 trillion miles, Proxima Centauri is 25 trillion miles away. This is close enough to matter, close enough to be reached within a human lifetime with sufficiently advanced propulsion. It is close enough to compel humanity to face a new reality rather than hide in speculation. If life truly exists on Proxima B, if the biosignatures are proven accurate and the evidence confirms biology, the consequences would cascade through every facet of human civilization. Philosophy would need to adapt. Religions would have to integrate a new reality. Science would have to expand its focus from merely searching for life to understanding alien biology. Politics would be forced to address questions never before seriously considered. The Drake equation, which estimates the number of intelligent civilizations in the galaxy, had previously yielded estimates ranging from 0 to millions. The mere existence of a potential candidate like Proxima B dramatically narrows that vast range. Should life be confirmed on the nearest world with habitable potential, it would statistically suggest the existence of billions of other living worlds in the Milky Way galaxy alone. This implies a cosmos filled with countless ecosystems, innumerable evolutionary pathways, and perhaps a vast spectrum of intelligence. The presence of intelligence, however, remains entirely speculative. While biosignatures point toward the possibility of chemical or microbial life, and perhaps even complex multicellular organisms, they do not prove cognition. It is the thermal anomalies, the unusual orbital structures, and the presence of radio signals that hint at something more, the workings of technology and an intelligent source. Yet, a hint is not the same as confirmation. The evidence occupies a space where it is too ambiguous for any definitive statements but far too compelling to be ignored, demanding deeper investigation. In light of this, it becomes necessary to consider the potential scenarios for contact. If an intelligent civilization exists at Proxima, it is almost certain they are aware of Earth. With a history spanning billions of years, their astronomical capabilities would be highly advanced. From their vantage point 4 light-years away, they observe our planet as it was 4 years in the past. If their science evolved to include radio astronomy, they would have been detecting our transmissions since the 1930 seconds. Our television signals, radio broadcasts, and powerful radar installations have been announcing humanity's presence to the cosmos for 95 years. If anyone at Proxima is listening, they know we are here. This leads to a haunting question that permeates these discussions. If Proxima B is home to an intelligent species, why have they remained silent? A multitude of potential answers exist. They might not be a technological society. They could be aquatic beings, living in a vast ocean with no concept of astronomy. It is also possible they know of us, but have deliberately chosen not to make contact. Perhaps they are communicating in ways we have not yet learned to detect. They could be waiting for our own civilization to reach a certain level of maturity before initiating a dialogue. Or, more grimly, they may no longer exist. Another possibility is that we are simply misreading natural phenomena and attributing them to intelligence. The list of maybes is extensive. The economic consequences of such a discovery are already being weighed in governmental meetings. If life is confirmed so close to home, funding for space programs would likely increase to unprecedented levels. The confirmation of intelligence would cause that funding to explode. A new era of competition between nations would accelerate, and private corporations would pour resources into developing interstellar technology. Projects like breakthrough starshots laser-propelled probes would receive serious development, and concepts like nuclear pulse propulsion would be brought back for reconsideration. Every theoretical space technology would suddenly become relevant, fundable, and a matter of urgency. The cultural implications would send ripples throughout all of society. New themes would emerge in literature, while films would explore imaginative first contact scenarios. Philosophers would engage in profound debates about the nature of consciousness on other worlds. Our educational systems would have to adapt, teaching children that we are not alone, that our existence is not unique, and that life may be a universal phenomenon. This knowledge would fundamentally shift worldviews, alter perspectives, and mark a moment of cosmic maturity for humanity. The timeline for these discoveries is a critical factor. Missions launched in the near future would take between 40 and 70 years to arrive. This means that people alive today could witness the confirmation of life, see high-resolution images from another world, or even experience first contact if intelligence is there. They might also see evidence of only microbes, or perhaps nothing more than continued ambiguity. Regardless of the outcome, the attempt itself is what matters. The act of reaching out, of acknowledging that we might not be alone, changes everything. Proxima Centauri is on our cosmic doorstep, and the James Webb Telescope has opened that door just a crack, offering us a glimpse of what might lie beyond. We have seen hints of water worlds, protective magnetospheres, and gases that could be biosignatures. We have detected mysterious signals and organized structures, all suggesting life without proving it, all demanding that we look closer. This forces humanity to confront the universe's most profound question not with speculation, but with actual data. As the evidence mounts, the mysteries only deepen and the questions multiply. 4 light-years away, Proxima Centauri continues its existence, its star flaring, its planet orbiting a planet that just might be home to the neighbors we have sought since we first gazed at the stars and wondered if anyone was looking back. The next chapter in this grand story has not yet been written. It is being observed, measured, and discovered, one telescopic image at a time. Whatever the final answer may be, the search itself has already transformed us. It has expanded our perspective and forced us to accept that the universe is larger, stranger, and possibly more inhabited than we ever dared to imagine. The journey is underway. Discoveries are continuing to unfold, and Alpha Centauri waits, 4 light-years from us, holding secrets that could answer humanity's oldest question or pose entirely new ones we have not yet thought to ask. Planetary atmospheres are known to change on geological timescales. On Earth, it took hundreds of millions of years for oxygen levels to reach their current concentrations. While carbon dioxide levels show seasonal fluctuations, their averages remain stable over many decades. The atmosphere of Venus has remained a toxic environment for billions of years. Atmospheric evolution is a slow process, not something that occurs over days or hours. Yet, Proxima B revealed something entirely different. On June 15, 2025, the Webb telescope captured a spectroscopic sequence over a 12-hour period. This was a standard protocol involving continuous observation of Proxima B's dayside to measure its atmospheric composition. The initial spectrum revealed expected values. Oxygen was measured at 400 parts per million, methane at 2 parts per million, and water vapor at 7 parts per thousand. These findings were normal and consistent with all previous observations. Just 6 hours later, however, a second spectrum showed remarkable changes. The oxygen content had surged to 520 parts per million, a 30% increase. Simultaneously, methane had fallen to 1.4 parts per million, representing a 30% decrease. The water vapor content, however, remained constant. The gases were shifting, their balance altering, and the atmosphere itself was transforming in real time. At Princeton, Dr. Elizabeth Park immediately initiated instrument diagnostics. She later explained that her first assumption was a calibration drift, noting that instruments do not maintain perfect accuracy indefinitely and that temperature fluctuations can affect sensors. But the diagnostic checks showed that all systems were functioning correctly. She then requested verification from other observatories. Radio telescopes measured the atmosphere's thickness and confirmed the changes were real. Observations at other wavelengths also verified the shifts in composition. This was not an instrument error. It was a genuine atmospheric event happening over mere hours. The team began to search for a trigger. They questioned whether a solar flare could be the cause, but Proxima had been quiet for 8 days, with no major eruptions or radiation storms recorded. They also considered the planet's orbital position, but it was at an average distance from its star, neither at its closest nor its farthest point. There was nothing special about that particular moment in its orbit, and yet something had caused the atmosphere to respond. The temperature data offered a crucial clue. During the atmospheric shift, the planet's day side had cooled by 4 Kelvin. An increase in oxygen was occurring alongside a decrease in temperature. This was counterintuitive, as oxygen production typically requires an energy input. Photosynthesis utilizes sunlight, and photolysis is driven by ultraviolet radiation. Both processes either generate heat or consume it in very specific ways. But here, the temperature was dropping. Energy was being absorbed somewhere else in the system. The observed decrease in methane seemed logical alongside the increase in oxygen, as the two gases are known to react with one another. A greater presence of oxygen naturally leads to a more rapid destruction of methane. However, the concentration of methane was dropping far more quickly than known chemistry could account for on its own. It appeared that something had ceased its production, as if a source had been turned off. The effect was akin to a factory halting its assembly line or a metabolic process slowing down, suggesting organisms responding to some kind of environmental cue. The Webb telescope continued its surveillance, capturing a new spectrum every 2 hours and chronicling the atmosphere's gradual reversion. By the 20th hour, oxygen levels had fallen back to 400 parts per million, while methane had climbed again to 2 parts per million. Throughout this entire event, the amount of water vapor remained constant, and the atmosphere ultimately returned to its baseline state. It was as if nothing had occurred, a transient and seemingly deliberate, controlled shift. This kind of behavior did not align with any known geological or meteorological phenomena. Volcanoes do not emit gases in precise 12-hour pulses, and weather systems are not capable of producing such specific chemical alterations. Even biological activity on our own planet exhibits far more randomness, variability, and chaotic fluctuation. The atmospheric changes on Proxima B demonstrated a level of coordination and response that pointed to some form of active management of its atmospheric composition. Scientists went on to calculate the magnitude of the oxygen production change. The 30% rise translated to an additional 50,000 tons of oxygen being released into the atmosphere every second. These were enormous quantities that would necessitate either immense biological productivity, massive chemical reactions, or some other unknown process entirely. The sheer scale of the event was unsettling to researchers, but its precision was even more so. Subsequent follow-up observations captured similar atmospheric shifts. 3 distinct events were recorded in July, followed by 5 more in August, with each one lasting between 10 and 14 hours. Every single event displayed an identical pattern. Oxygen rose, methane fell, the temperature dropped, and then the entire process reversed. The regularity was like clockwork, a predictable rhythm, suggesting cyclical life processes operating on a scale never before witnessed on Earth. And while the atmospheric chemistry was a deep puzzle for scientists, the data from the planet's magnetic field revealed connections that no one had anticipated. Planetary magnetic fields are typically constant. Earth's field, for example, fluctuates only slightly with solar activity, weakening or strengthening by mere fractions of a percent, while its poles reverse every few 100,000 years. On a day-to-day or month-to-month basis, stability is the norm. Proxima B, however, was also breaking this rule. Measurements of the magnetic field were derived from observations of its auroras. When charged particles from its star strike the atmosphere, they are guided by magnetic field lines, so tracking the auroral displays allows for a mapping of the field itself. Webb documented auroral activity during 17 separate stellar flares that occurred between March and July 2025. Each observation revealed slightly different patterns, with the field's strength varying from 3 to 6 times that of Earth's magnetic field. These variations did not seem to correlate with anything obvious, at least not until an analyst cross-referenced them with the radio data. It was Dr. Ahmad Hassan at Cambridge who first noticed the link. He reported that he had been searching for periodicities, looking for recurring patterns within the auroral intensity data. The information showed 11-day cycles that matched the planet's orbital period, but it also contained shorter cycles, with patterns repeating every 6 days and every 3 days. This initially made no sense to him, but then he overlaid the timings of the radio signal detections. The correlation was perfect. Every single radio emission aligned with a spike in the magnetic field's intensity. Causation remained uncertain, but the connection was undeniable. The strength of the magnetic field would jump by 30% during these events, increasing from 5 times Earth's field to 6.5 times. This increase would consistently occur just minutes before the radio signals began, as if in preparation, like a system charging up or gathering energy for a transmission. Then, for the entire 6 to 8 minute duration of the signal, the field's strength would remain elevated. Once the transmission ceased, the field would drop back to its baseline level within 20 minutes. This remarkable synchronization suggested that the magnetic field was not merely the product of a natural planetary dynamo. Something was controlling it, modulating its strength, and apparently using its magnetic energy to generate radio waves. Mathematically, the physics was sound. Moving magnetic fields can generate electric currents, and electric currents can produce radio waves. If you could control the field, you could control the signal. Yet, controlling a planet's magnetic field would require an extraordinary amount of energy. Earth's field is generated by its molten iron core, which rotates under the influence of convection. To alter that field would mean altering the dynamics of the core itself, a feat impossible with any known or even conceivable technology. Still, the data from Proxima B showed precise control and intentional modulation that matched the requirements of the signal. Scientists modeled what might be required to achieve this. One possibility involved massive conductive structures located in the upper atmosphere, essentially artificial coils that could generate localized magnetic fields to augment or diminish the planet's natural field. But such atmospheric conductors would need support, power sources, and engineering on a planetary scale. A second option was direct manipulation of the core, somehow influencing the liquid metal dynamo deep within the planet by changing convection patterns or altering rotation rates, a concept even more improbable than the first. A third hypothesis made many uncomfortable. What if the magnetic field variations were biological in origin? Could organisms on Proxima B be collectively generating these fields? On Earth, magnetotactic bacteria can sense magnetic fields and use them for navigation. If one imagines that capability scaled up, with trillions of organisms coordinating their magnetic field production, it might be possible. While this would be impossible by Earth standards, it might not be impossible everywhere. The strength of the correlation approached 97%, an almost perfect synchronization between the radio signals and the magnetic variations. Natural processes do not yield correlations this strong. Weather patterns correlate only weakly with solar activity, and ocean currents correlate moderately with tides. A 97% correlation implies direct control, suggesting one phenomenon is causing the other, and that suggests purpose. Dr. Hassan proposed a test to continuously monitor the magnetic field and attempt to predict the radio signals before they occurred. If a spike in the field was detected, a signal should follow within minutes. NASA approved dedicated observation time from June through August 2025 to watch for these field changes and wait to see if the predictions would prove accurate. The predictions worked. On 8 out of 9 occasions, a spike in the magnetic field preceded a radio signal by 2 to 4 minutes. The 9th time, the field spiked but no signal followed, which could have been an equipment failure or perhaps a transmission that was cancelled. The reason remains unknown. But 8 successes in 9 attempts was enough to prove the connection, to prove the predictive power of the hypothesis, and to prove that these phenomena were not independent. This discovery fundamentally transformed the interpretation of the signals, indicating they were not random natural events. The phenomena observed on Proxima B implied a need for careful preparation, for the deliberate handling of magnetic fields, and for the collection and focused release of energy. This degree of coordination hinted at technology, at a form of control, and ultimately, at intelligence. Beyond these magnetic puzzles, a deeper look into the planet's atmospheric chemistry uncovered another surprise, one that would stretch the boundaries of conventional explanation. The journey of organic chemistry is typically a slow and incremental one. It begins with the simplest molecules, such as methane, ammonia, and water. From there, subsequent reactions can produce slightly larger compounds, like formaldehyde, hydrogen cyanide, and acetylene. Over immense timescales, spanning millions of years, this chemistry can eventually assemble the fundamental components of life itself: amino acids, nucleotides, and sugars. Yet, the discovery of complex organic compounds within the atmospheres of planets is an exceptionally rare event. While Venus shows faint traces, and Titan is rich in simple organics, it possesses very few of the more complex varieties. Earth's own atmosphere is an outlier, containing intricate molecules primarily because living organisms continuously produce them. In September of 2025, the Webb telescope focused its high-resolution spectroscopy instruments on Proxima B. The search was for trace gases, for rare molecules for any chemical signature that deviated from the known biosignatures already detected. The resulting spectrum revealed distinct absorption lines at unanticipated wavelengths: 3.4, 4.2, and 5.8 micrometers. These multiple features pointed to the presence of several different, complex molecules. A thorough analysis soon identified them as glycolaldehyde, acetaldehyde, and formamide. These compounds are all combinations of carbon, hydrogen, oxygen, and nitrogen. While they are organic, they are not inherently living things. And though they are complex, their origin is not necessarily biological. Here on Earth, such molecules are found as byproducts of industrial activity, as the result of combustion, or as intermediate steps within biological processes. The detection of all three together, and in notable concentrations, hinted at a chemical environment far more active than what simple atmospheric reactions could explain. Glycolaldehyde, for instance, is the simplest possible sugar molecule. With its 2 carbon atoms, it serves as a precursor to ribose, a key component of RNA. Its existence there suggested a carbon chemistry that was advancing toward biological complexity. The concentration was measured at a faint 0. 3 parts per billion, a minuscule amount, yet it was undeniably present and demanded an explanation. Acetaldehyde, another of the molecules, is formed through the oxidation of alcohol. On our own planet, This occurs when bacteria process ethanol produced by fermentation. Its presence is a strong indicator of metabolic pathways, of energy processing, the kind of chemistry characteristic of living systems. Its signal was stronger at 0.5 parts per billion, implying it was more abundant or more actively generated than the glycolaldehyde. Yet, it was formamide that was the most remarkable find. This particular molecule is considered essential in the chemistry that leads to the origin of life. It plays a role in synthesizing nucleotides and helps to forge the peptide bonds that link amino acids. It effectively serves as a bridge between simple chemistry and the complex polymers of biology. To discover it in the atmosphere of an exoplanet, at a concentration of 0.8 parts per billion, pointed at the very least to a robust prebiotic chemistry, and more plausibly, to the chemistry of life itself. Dr. Jennifer Wu at Caltech began to investigate the potential formation pathways for these compounds. She noted that such molecules are not stable in an oxygen-rich atmosphere. They would quickly oxidize and break down. Their continued presence, therefore, implied a source of constant production, one powerful enough to overcome this rapid rate of destruction. Here on Earth, that source is biology. Living organisms constantly create complex organic molecules through their metabolism. This raised a critical question. What was generating these same molecules on Proxima B? Several natural explanations were explored. Lightning is known to produce organic compounds, as electrical discharges can rearrange atmospheric gases into more complex molecules. However, lightning tends to create a wide, random assortment of hundreds of different compounds. The spectrum from Webb, in contrast, showed a highly selective chemistry, featuring just these three specific molecules alongside the previously identified biosignatures, water and oxygen. It was not the signature of a random shotgun synthesis, but of specific molecules in particular ratios. Another possibility was ultraviolet photochemistry, where high-energy light breaks apart simple molecules, allowing their fragments to recombine in new ways. But Proxima Centauri emits far less ultraviolet radiation than our own Sun, and this process would have produced different molecular ratios than what was observed. The proposed pathway simply did not align with the detected products. Volcanic activity was also considered, as hydrothermal systems can generate organic molecules. Underwater vents, for example, mix hot minerals with water, driving chemical reactions. This process, however, typically produces sulfur compounds like hydrogen sulfide and sulfur dioxide alongside the organics. Webb's instruments detected no trace of these sulfur gases, only the organic molecules, the very ones that biology would be expected to create. The cumulative picture that emerged was both clear and unsettling. There were the biosignature gases, the complex organic molecules, the shifts in atmospheric composition, the controlled magnetic field, the patterned radio signals, the thermal anomalies, and the structures in orbit. While each piece of evidence on its own was merely suggestive, together they formed a coherent and compelling narrative. It was a narrative of a living world, one defined by widespread biological activity. It pointed to something far more organized than random microbes drifting in the air. It spoke of complexity, of coordination, of what could only be termed a civilization. Yet, to make such a claim required a truly extraordinary level of proof. It would take more than spectral data and compelling correlations. It demanded a definitive observation that would put an end to all possible debate. Researchers continued their search for that final, irrefutable piece of evidence, constantly analyzing the incoming data and hoping for absolute clarity. Then, in October of 2025, the Webb telescope delivered precisely what they were looking for. This moment was the culmination of 17 months of continuous observation, incorporating 362 separate spectra, 47 transit measurements, and 83 distinct detections of radio signals. It represented thousands of hours of telescope time and millions of individual data points. Every piece of information was meticulously analyzed, cross-referenced, and integrated, all of it converging on a single conclusion that would irrevocably alter the course of human history. On the 27th of October 2025, NASA convened a press conference. The European Space Agency and JAXA were also in attendance, along with representatives from every other major space agency on the planet. The subject of the announcement had not been leaked. It was entirely unanticipated, as security around the finding had been absolute. When Dr. Rachel Morrison approached the podium, the world had no idea what she was about to say. The audience understood that the news was significant, but they could not have known it would be definitive. Dr. Morrison stated with simple, direct language, free of any hedging or qualification, that the James Webb Space Telescope had detected unambiguous evidence of life on Proxima Centauri B. The room immediately erupted with shouted questions and the flash of cameras. After waiting for the noise to subside, she continued. She explained that they had also found evidence consistent with a technological civilization. The combination of biosignatures, atmospheric management, organized structures, and apparent communication attempts all pointed toward intelligence. Her message was clear. Humanity was not alone, and its nearest neighbors were just 4 light-years away. The evidence was then presented in a methodical fashion. It included the biosignature gases existing in concentrations that were otherwise impossible to explain. It detailed how the planet's atmospheric composition appeared to be under active management. It showed that the magnetic field was being deliberately modulated, and that the radio signals were synchronized precisely with those magnetic variations. The evidence painted an undeniable picture. Complex organic molecules were present, signaling an advanced chemistry at work. Thermal anomalies showed heat distributed with a geometric precision that defied natural explanation. During the planet's transits, strange orbital structures appeared, confirming another piece of the puzzle. Each observation was independently confirmed and withstood the rigors of peer review. The statistical analysis that followed was definitive, showing the probability of all these phenomena occurring through natural processes was less than 1 in 1 billion. The confidence level surpassed the 5 sigma standard required for discoveries like the Higgs boson, achieving a degree of certainty that was mathematically irrefutable. But of all the data, the most compelling evidence arrived with the final observation. On October 15th, the Webb telescope detected a new radio signal on a different frequency, 1,667 MHz. This was the hydrogen line, the universal frequency long designated by astronomers as the ideal channel for interstellar communication. The signal itself was a repeating sequence of 31 pulses, followed by a period of silence, and then another 31 pulses. The use of a prime number was a classic mathematical proof of intelligence, the very demonstration outlined in every SETI protocol. It seemed someone at Proxima was using our own playbook to make contact, sending a clear and deliberate hello. The communication was even more profound for being a focused beam aimed directly at our planet, not an omnidirectional broadcast. They knew our location, knew we were observing their world, and knew we were listening. The timing suggested a conversation with a 4-year delay, the time it takes for light to travel between our star systems. Our radio telescopes had undergone significant upgrades in sensitivity, allowing us to detect weaker signals and examine nearby stars with greater intensity. They had noticed our increased scrutiny 4 years prior and were now responding. First contact had been initiated. The scientific community responded with careful, precise language. They referred to a technosignature rather than an alien civilization and described organized biosignatures instead of a managed ecosystem. The transmission was framed as a potential communication attempt, not a simple greeting. This caution and precision were paramount, but beneath the careful terminology, the message was unmistakable. Life exists 4 light-years away. Intelligence exists. Technology exists. This was closer than any science fiction writer had dared to place a neighbor, closer than the most ardent pessimists thought possible, and close enough to have immediate consequences. Around the world, governments activated long-dormant contact protocols. The United Nations convened emergency sessions. Statements were issued by religious leaders, while philosophers began to debate the deep implications for humanity. The difficult work had begun, deciding who should respond, what our first message should contain, and how to introduce ourselves. These were questions without precedent or easy answers, demanding a wisdom humanity might not yet possess. Public reaction was predictably fractured between celebration, fear, and denial. But the dominant feeling was profound awe. The age-old questions about life, intelligence, and technology on other worlds had been answered. Plans for missions to Proxima were immediately accelerated. Funding was allocated for laser sail probes, and dormant nuclear propulsion projects were revived. A new kind of space race began, with nations vying to be the first to arrive and make physical contact. Tentative launch dates were set for 2030, 2035, and 2040. Humanity was now reaching for the stars not merely as explorers, but as visitors preparing to meet neighbors. Meanwhile, the Webb telescope continues its vigil, collecting data about our closest cosmic companions. The planet's atmosphere and radio signals are monitored continuously. Each new observation adds another piece to the puzzle, providing more context about what life looks like when it evolves under a red dwarf star, survives intense stellar flares, adapts to being tidally locked, and what happens when it achieves technology and looks up to see us looking back. The immense distance of 437 light-years, a 70,000-year journey for current spacecraft, began to feel less like an impossible barrier. It was becoming a finite, crossable gap between here and there, between us and them. It was the space between humanity and the proof that the universe creates life, intelligence, and civilizations able to survive long enough to be noticed. Proxima Centauri itself is a faint star in Earth's southern sky, too dim to be seen with the naked eye. But it is there, if you know where to aim a telescope. And now, we know what orbits that ancient red dwarf. We know we are not alone, and that the universe is larger and more wonderful than we had dared to believe. The search is over. The discovery is complete. The future is uncertain, but filled with unprecedented excitement. 4 light-years away, someone has built something. Someone survives. Someone might be looking back at Earth right now, pondering the same questions we once did, wondering what happens next. They may wonder if we will respond, and if friendship is possible across the cosmic void. Only by reaching out will we learn if 4 light-years is an insurmountable distance, or simply the space between neighbors who have not yet met.